Hello, my name is Eric Westra. Welcome to the course Introduction to QGIS Python Programming by Pact Publishing. I've been developing software for a long time and have worked almost exclusively in Python for 15 years, though in the last year or two I've also been developing phone apps using JavaScript and Objective-C. In the 1990s, I developed one of the world's most sophisticated systems for running urgent messenger delivery companies, then turned my attention to building a high-volume geocoder consolidating online classified ads. More recently, I've been working on developing iPhone apps that capture and record the user's location, both as a guide for cyclists and to detect possible fraud when making online transactions. I'm also the author of several books, including Python Geospatial Analysis, Building Mapping Applications with QGIS, and Modular Programming with Python, all published by Pact Publishing. This course provides an in-depth introduction to writing geospatial programs using QGIS and Python. You will learn about QGIS itself, the underlying PyQGIS API, and how you can access this API from Python code. You will learn how to write code interactively using the QGIS Python console, how to write plugins for QGIS, and how to create standalone mapping applications using Python that build on the PyQGIS libraries. This video provides a summary of the entire course. There are 6 sections in this course. The QGIS system. You will learn about the QGIS application itself and how you can interact with it using Python code. The QGIS Python console. You'll learn all about using the built-in Python console window to enter and run Python code. Understanding the PyQGIS library gives you an in-depth introduction to the Python libraries built into QGIS, how to understand and work with them, and the main classes and packages you'll need to become familiar with. Using the PyQGIS library, we'll see how you can use PyQGIS to solve a range of real-world geospatial programming challenges. Creating QGIS plugins looks in detail at the process of developing Python plugins that extend the functionality of the QGIS system. Using QGIS in an external application covers the process of developing standalone mapping applications using Python and the PyQGIS library. By the end of this course, you will be confident in using QGIS and Python to read, write, analyze, and manipulate geospatial data. You'll know how to extend the functionality of QGIS using Python plugins, and you'll be able to develop your own standalone mapping applications built on top of the PyQGIS library. To work through this course, you will need to be an experienced Python programmer. You'll need to have a reasonably modern computer running MS Windows, Mac OS, or Linux, and you'll also need a reasonably fast internet connection, as some of the files we download are rather large. Note that you don't need to know anything about QGIS itself, or even geospatial programming, as we'll teach you everything you need to know. Let's go.
Hi, and welcome to the installation and setup video for this course. There isn't a lot of setting up you need to do, but you do need to install a couple of programs, so let's work through the details. Because the way you set up your computer to develop programs using QGIS and Python will vary depending on which type of operating system you are running, we're going to need to look at each one separately. For MS Windows, you'll need to use a special installer. For Mac OS, there's a great website that we can use to download all of the required files. And for Linux, use the built-in package manager to do all the work. For Microsoft Windows, you'll need to use a special installer that combines QGIS with a Python interpreter and all of the required libraries. This is called the OSGeo4W installer. You can download this installer from this website. Here's what this looks like. OSGeo4W is a Windows installer for all sorts of geospatial-related libraries and tools. You don't want to install everything using this installer, as some of the packages require extra software before they can be used. Instead, just download the installer, that is the 32 or 64-bit files available here, and follow the instructions that are on this web page. When you're asked which packages to install, just select QGIS and Python. These two programs and their required libraries will then be installed for you automatically. For Mac OS, we're going to use something called the King Chaos website. This site provides Mac OS specific versions of all sorts of geospatial libraries and tools. Now, when we go to this website, we want to go to the software downloads link and then Unix porting downloads. This is geospatial software for Mac. And finally, we're looking for QGIS. Now, the QGIS installer, this one here, includes QGIS itself along with all of the libraries that you'll need. You're going to be using the system Python built into the Mac operating system, so you don't need to install Python separately, but you will need to install several libraries in order to get it to work. Let's see how this works. File we downloaded. Now, because this installer was written by a non-certified developer, you're going to need to hold down the Control key and select Open from the pop-up menu to open it. If you don't do this, you'll get a security warning telling you that you can't open the file. Now, you see there's lots of bits to this download. We're interested in the README file here, which gives us all the information we need. Now, it tells us that we need to install these packages here before we install QGIS. So you just have to do the installation in order. GDAL complete, NumPy, matplotlib, and finally QGIS. Just follow these steps one at a time and you'll have everything installed. Now, for Linux and similar machines, you'll need to follow the installation instructions on the main QGIS website. For Linux and similar machines, you'll need to follow the installation instructions on the main QGIS website. We just scroll down here, download now. We're interested in the Linux installation instructions, and you can see that there's instructions here for each type of Linux distribution. So just select the flavor of Linux that you're using, and you can follow these instructions to install QGIS and Python onto your computer. In this video, we looked at the steps you need to follow to get your computer set up to develop geospatial applications using QGIS and Python. As each operating system has its own installation process, we looked separately at the steps involved in installing on MS Windows, Mac OS, and Linux. In the next section, we will start to learn about the QGIS application itself so that you can become familiar with it before you start writing code.
Hi, welcome to this section of our video course. This section is called the QGIS system. In this section, we will learn about the QGIS system itself, see how it is organized and how Python forms a major part of QGIS under the hood. We will look at the 3 ways in which Python can be used to interact with QGIS: by using the QGIS Python console, by writing a Python plugin for QGIS, and by writing a standalone application that uses the QGIS Python API. We will look at a simple example of each of these so you can see what is involved in using each development option. Because you don't need to have any prior knowledge of QGIS to complete this course, this first video is an introduction to the QGIS system itself. You will see how to use QGIS to display geospatial data, and we'll use this to learn how QGIS is organized internally. You'll need to know this before you can start programming with QGIS. In this video, we're going to start by downloading some sample data and then display that data using QGIS. This will show us how data sources and layers are used to create a map. We'll then see how to customize the way information is shown on the map and finish by saving your work into a QGIS project file. This will give us a good overview of QGIS before we start writing code. Okay, let's start by downloading some data. We're going to make use of a website called naturalearthdata.com. This site has a ton of high-quality geospatial data which you can download for free. We'll go to the download section, and we're interested here in the large scale 1 to 10 million physical data. And there are 3 files we want to download from this page. First of all, we want to download the land outlines, which is the outline of various land masses. Then the river and lake center lines, which is a line representing the center of each river.
And finally, lake outlines. It's the outline of all the lakes and reservoirs. Once we've downloaded these files, we'll end up with 3 zip archives. Each of these zip archives contains what's called a shapefile, which is a way of storing geospatial data. The various bits of the shapefile. Now that we've downloaded the data we need, let's use QGIS to display it. Now QGIS is a complicated program and it will take a few seconds to start up. Here's the QGIS window. Now let's load up a shapefile to see how it works. Go to Add, Vector Layer, Browse, and we'll start by loading .shp extension file for the land. And there we are. Now over here on the left under the Layers panel, you see there's an entry now for the data we just downloaded. And over here on the right in the map view, we can see the various polygons that are contained within that file. Now let's take a closer look at what the layer we just added to this system. Under the General tab, we have a layer source, which tells us where this data comes from. As you can see, it's referring back to the file that we just downloaded. Under Style, it shows us how that information is being displayed. In this case, it's using a sort of a greenish color. Let's use a slightly darker green here to show polygons. And here we go. You see we've changed the style. Now QGIS works a little bit like Google Maps. You can zoom in and out using these controls here, the plus and the minus buttons, or use the hand control to pan around. Let's zoom in here on an area of the west coast of the United States, the San Francisco Bay Area. There we go. You can get a good idea of what the data looks like and how detailed it is. Now that we've got looking at this area, let's go and add the other 2 layers that we downloaded earlier, 2 more vector layers. First of all, we're going to load up the lakes. And there we are, purple lakes, delightful. And then again, we're going to do another one here for the river center lines. And there we go. Now, what's interesting here, if you ever look closely here, see how the river is sitting on top of the lake. It kind of looks a bit funny, doesn't it? This is because of the order in which information is displayed by QGIS. The layers are always displayed from bottom to top. So the land is shown first, then the lakes, then the rivers. So let's change the order here. We drag that down. You can see now the river is sitting behind the lake, which looks a little better. So you can control the order in which information is displayed just by rearranging the layers. The other thing you can do is you can turn on and off your various layers using the checkboxes. Now there's one more final thing about QGIS that you need to know about. It's called the QGIS project. Everything we've been working on, the entire contents of the QGIS window, our various layers and how they are displayed, all of this is part of the current project within QGIS. QGIS can only ever have one project open at a time. If you want, you can save what you've done by saving your project file to disk. Now, when you've done this, it means that you can quit out of QGIS and then reload your project to get back to where you were before. So let's have a look at what we've learned. In this video, we downloaded some sample geospatial data and learned how to display it using QGIS. We saw how the data sources are external to QGIS and are referred to by the layers, which can be combined to generate the map. We saw how the layers can be rearranged to control the order in which the different data sources are displayed. We also saw how you can use the Layer Properties window to control how the data is shown. Finally, we saw how a QGIS project file stores your various data sources, allowing you to save your work and return to it later. This gives us a good introduction to the QGIS system. In the next video, we're going to see how Python forms a major part of the QGIS system and how we can use Python with QGIS as a powerful tool for writing programs that work with spatial data. In the previous video, we introduced the QGIS system and saw how you can use it as an application to display and work with spatial data. In this video, we will see how the Python programming language fits into QGIS. We'll learn about the QGIS Python console window, see how plugins can be used to extend QGIS's functionality, discover the rich and powerful API that QGIS provides for building your own geospatial applications, and see how this API can be accessed using Python. Let's start up the QGIS application. QGIS itself is written in C++, but includes extensive support for Python. In fact, it has its own Python interpreter built in, which you can access directly or use to run various Python programs and scripts. QGIS also comes with a comprehensive API which has Python bindings, so you can do almost anything you want in QGIS using Python. Here's the QGIS Python console. As you can see, this gives you direct access to the built-in Python interpreter. And just like any other Python shell, you can type Python code and have it run right away. For example, here we go. Oops. Of course, we can do this using the ordinary Python shell, but we can do lots more. For example, let's use the built-in QGIS Python API to do some calculations on a polygon. Here's the polygon we're going to work with. It's a simple triangle. Notice the coordinates for each of these vertices, 1, 1, 4, 4, 7, 1. We'll need these in a moment. We're going to start by loading in the QGIS geometry class from the API. So from QGIS.core import QGIS geometry. Now let's use that to create our polygon. One one 4 4 7 1 1 1. In this case, we've created the polygon by hand using a well-known text or WKT format string to define the coordinates that make up the polygon. Don't worry about the details of WKT if you haven't encountered it before. It's just a text format for defining shapes and locations. Now that we have our triangle, let's ask QGIS to tell us some things about it. We can do things like print the area of the triangle, or if we wanted to, we could go and print the length of it, which is the perimeter. Now we're not going to go into too much detail about the Python console right now, but you can see that Python is very much part of QGIS under the hood, and you can use it to do all sorts of things you wouldn't be able to do with just the ordinary Python shell. Another very exciting aspect of QGIS is the ability to install and use plugins. You've no doubt seen plugins in other programs such as Google Chrome or Adobe Photoshop. You can install plugins to extend and change the way a program works. In QGIS, plugins allow you to add features to the QGIS system, and as we'll see in a moment, there are hundreds of plugins available. Plugins can be written in either C++ or Python. Now let's download and install a Python plugin. We'll go to the bottom here and look at the Zoom to Point plugin. Let's install it. It only takes a second. Here we are, done. Now that plugin then appears in the plugins menu, and if we ran it, it would allow us to type in a latitude and longitude value and zoom the map to that point. But rather than using the plugin, let's have a look how it works inside. Now QGIS stores its plugins in a hidden directory. Let's go to this directory. And as you can see, we now have a Zoom to Point folder here, which contains the source code to the plugin. And let's open one of these files up. And as you can see, this is all Python code. So QGIS is using Python all the way down. Now later on, you'll learn how to write your own QGIS plugins using Python. But for now, let's take a closer look at the API which QGIS provides. we're going to be using this API an awful lot. Now, this is the documentation for the API, classes, and there are lots and lots and lots of different classes available. We're going to have a look at the QGIS geometry class we looked at earlier, and here's the definition for it. Now, down here we can go and have a closer look at the area function which we used earlier. So everything is documented here. Of course it's all documented for C++ programmers, not for Python programmers, but the same API can be used, and you can figure out how everything works by using this documentation. Now you're not just limited to using the Python built into QGIS. You can also call the QGIS Python API from external programs. To do this, we're going to have to set up a few environment variables so that the Python interpreter can find QGIS. Now that we've done that, start up Python interpreter, and just like we did within the built-in Python console, we can use the QGIS API. So let's just create our triangle. QGIS geometry KT 11447111. And again, we can access the complete API from within the Python interpreter. Now, if you want to use the full QGIS API from an external program, or if your program is using a GUI, there's a little bit more work to be done, but we'll look at how to do that in a future video. In this video, we saw how Python forms a major part of QGIS and how we can access and control QGIS using Python code. We saw that QGIS has its own built-in Python interpreter, which we can access using the QGIS Python console. We also saw how we can extend QGIS's functionality by installing plugins which can be written in Python. We also learned about the comprehensive API that QGIS provides and saw how we can access that API from our Python programs. Finally, we discovered that you can use your regular Python interpreter to access QGIS and use this API from within an external program. In the next video, we will learn more about the Python console built into QGIS, and we'll see how you can use the Python console to explore and control the QGIS system. Welcome back. In the previous video, we saw the three ways in which Python can be used to work with QGIS: by using the QGIS Python console, by writing plugins, and by writing external applications that use the QGIS Python API. In this video, we will take a closer look at the QGIS Python console to see how it can be used to interact with the QGIS system. We'll load a map into QGIS using Python and see how we can manipulate that map using Python code. Finally, we'll use the Python console to do some calculations using geospatial data. In this video, we're going to use a set of country outlines called the World Borders Dataset. This is a very useful geospatial data source, so let's download it. It's in a site called Thematic Mapping. Down here we have the World Borders Dataset. Now we want to download, where is it? There. The full version there. Once we've downloaded this file, it comes again in the form of a zip archive, a shapefile that's compressed. So we need to decompress it so we can access it. Now, in an earlier video, we created a map using various commands within QGIS. We're now going to do the same thing again, except this time we'll use Python code. We'll start with a blank project and open up the Python console window. To add a shapefile to the current project, we're going to use a variable called iFace. iFace is set up automatically by the Python console to give you access to the QGIS user interface. In this case, we want to add a vector layer and we need to tell QGIS where our data source can be found. The next thing we need to do is tell QGIS which layer within the data source we want to use. In this case, the layer is called TM World Borders 0.3. Finally, we want to tell QGIS which library to use to load it in. In this case, we're using the OGR library. And there we go. As you can see, we've now loaded the shapefile into QGIS. As you can see, this dataset contains all of the country outlines, and it's quite a useful dataset, and I've used it a lot in my own geospatial development work. Now let's zoom in on an area of California so we can see what our shapefile looks like in more detail. Once again, we'll use the iFace variable, but this time we're going to need to use something called the map canvas. The map canvas object represents the area of the window where the map is drawn. In this case, we want to set the extent of the visible area of the map. So to do that, we use a QGIS rectangle, and we have to type in the latitude and longitude coordinates for where we want to be. There we are. It doesn't look very good though, does it? That's because we have to tell QGIS to refresh the map once we change it. So once again, we use the iFace variable, the map canvas, and we tell it to refresh itself. That's better, isn't it? Now let's change the color that QGIS uses to draw the background onto which our country outlines are drawn. To do this, we'll need to use the QColor class from the PyQt library. So from PyQt4, here we are. QGIS is written using the Qt library, and PyQt is a Python wrapper around Qt. To set the background color, we'll need to update the map canvas, setting the canvas color to the color we want. Once again, we're going to need to refresh. And as you can see, we've set the background color to blue. Let's finish our introduction to the QGIS Python console by using it to perform some simple geospatial analysis using Python. We'll iterate over all the countries in the world borders dataset and print the name and centroid or centermost point for each country. We already have a reference to our world borders dataset map layer in the variable called layer. We can use this to iterate over the various features in the layer. Once we have the feature, we need to get the geometry associated with it. Once we have the geometry, we can ask it to calculate the centroid. Now, because the centroid function returns a geometry object as the centermost point for the coordinate, we're using the asPoint function to convert this into a coordinate. Finally, we want to get the name of the country, which is stored in an attribute called name. With all this information, we can now print out the name and centroid value for each feature. Let's run our program, and here we go. As you can see, the Python console isn't the fastest for printing out information, but it's calculating and displaying the name and centermost point for every country in the world. Now there's a lot more we could do with the console, of course, but this gives us a taste of what we could achieve. In this video, we have downloaded the World Borders dataset and used the Python console to display that dataset in the QGIS system. We saw how the iFace variable gives us access to the QGIS user interface, and how we can use the map canvas function to access and manipulate the map. We then used the Python console to iterate over the various countries and perform a simple geospatial calculation on each country. This completes our initial exploration of the Python console. In the next video, we will see how Python plugins work within QGIS. We will take a closer look at how a Python plugin is organized and what is involved in creating your own QGIS plugins using Python. Hello again. In the last video, we saw how the QGIS Python console can be used to run Python code to control and work with QGIS. However, a Python console is limited in that you have to type the instructions in one at a time. You're more likely to be interested in writing programs that integrate with QGIS, and that's exactly what a Python plugin will let you do. In this video, we will take a closer look at the Zoom to Point plugin we downloaded earlier. We'll see in more detail how this plugin works, how it uses a Python class to define the plugin's behavior, and how a class factory registers the plugin's class with QGIS. We'll see how this plugin can add and remove itself from the QGIS user interface, and what happens when the plugin is run. Finally, we'll see how the user interface for the plugin is created using a dialog and user interface template. When you download and install a plugin, QGIS stores the plugin in a directory within the hidden .qgis2/python/plugins directory. Note that the name of this hidden directory can vary depending on your operating system and which version of QGIS you're using. You might need to look for something called .qgis or whatever. Now here's the plugin we downloaded earlier. As you can see, the plugin is made up of a number of different files, all stored within one directory. First, there's the init.py package initialization file. Inside here we have class factory function. This class factory is used to register the plugin with the QGIS system. In this case, it's creating an instance of a class called Zoom to Point, which represents the plugin itself. Notice how the iFace variable, which we saw earlier when using the Python console, is passed into the class factory. This gives the plugin access to the QGIS system's user interface. Now let's take a look at that Zoom to Point class. Here it is. This class defines 4 methods. Let's look at each of these methods in turn. First of all, init. This is the initializer for the class. As you can see, this stores the iFace variable as an instance variable, so that it can be accessed later to access the QGIS system's user interface. Next, we have the initGUI method. This is used to add the plugin to the QGIS user interface. Here the plugin is setting up an action which calls self.run when the action is performed, and then it links that action to a toolbar icon and a menu item. This means that the run method will be called when the user selects the plugin or uses the toolbar or menu. Next, we have the unload function. This method is called when the user uninstalls the plugin. As you can see, this code is removing the action from the menu and the toolbar. So it takes away the plugin, makes the plugin disappear. Finally, we have the run method. This is called when the user runs the plugin. When the plugin is run, plugin will create a Zoom to Point dialog object. It then sets up this dialog, filling it with various values, and displays it to the user. If the user presses the OK button, then the plugin will extract the information the user has entered, and we'll use this to calculate a rectangle representing the area of the world that the user wants to see. It then updates the map canvas to display the appropriate area, and finally it saves away the values the user entered so that it can be used again the next time the plugin is run. Now let's take a closer look at the Zoom to Point dialog class. This class is a dialog, which is a window that displays on the screen with some contents. As you can see, the Zoom to Point dialog is a subclass of QDialog, which is defined within the Qt library's GUI package. When the dialog is initialized, the contents of the dialog is defined by a UI Zoom to Point class. This is the user interface definition for the contents of the dialog. So let's have a look at that. UI zoom to point.py. Here it is. There's a lot of detail in this class here, as you can see. And while you can write these UI files by yourself, it's much more common to generate them from a template, and that's what was done here. So let's have a look at the UI template that was used to generate this file. Now this program here is Qt Designer, and it's used to lay out various user interface templates. Now, as you can see, our dialog has various input fields and labels and buttons all nicely laid out. All of this information is stored in the UI file, which is an XML format file. And this template is then compiled using the Qt command line tools into the UI zoom to point.py file we saw earlier. Now, you don't have to use Qt Designer to create template files if you don't want to. It's quite possible to create the UI Python class by hand. But in this case, the authors have used Qt templates to define the user interface. So let's see how this template is used. Here we have an input field labeled X. Over here, that input field is given the name Xcode. Now, if we go back here to our dialog, you'll see that the UI zoom to point user interface was stored in an instance variable called UI. And that allows the plugin to refer to the various input fields like this. Here we have it. So dialog.ui.xcode. So xcode is the name of the object within the template. The UI template is UI within the dialog box. In this way, the input fields are part of the user interface, which is then used by the dialog, which is then used by the plugin. So you can see how all these various parts fit together. In this video, we took a much closer look at the Zoom to Point plugin and learned in more detail how plugins work. We learned about plugin class files and how they are registered with QGIS. We saw how plugins can add themselves to the QGIS user interface and what happens when a plugin is run. Finally, we saw how the plugin's own user interface can be created using dialogues and user interface templates. In the next video, we will see how you can access the QGIS Python APIs from your own Python programs to create standalone applications that run outside of QGIS. Hi! In the previous video, we saw how Python plugins can be used to extend the functionality of the QGIS system. These plugins integrate into the QGIS user interface and can create their own user interface using dialogues and other Qt building blocks. In this video, we'll see how to write a standalone Python program that runs outside of the QGIS system, but still makes use of the QGIS Python APIs. We will learn how to configure your Python setup to access the QGIS Python APIs. We'll see how applications that use these APIs need to be structured, and we'll finish by creating a simple standalone map viewer application. Ordinarily, a Python program isn't able to access the QGIS Python APIs. By the way, we're going to start using the name PyQGIS for these APIs. This is the name used by the QGIS documentation, and it's easier to say. So, in order for a Python program to access the PyQGIS APIs, we'll need to set the Python path and some environment variables so that Python can find the library and other files it needs. Unfortunately, because of differences in the way operating systems work, the way you do this will vary depending on which operating system you're using. Now there's a file called pythonsetup.txt in the example code for this video that includes all of these setup instructions for the various operating systems. Because I'm using a Mac, I'll set up my Python installation in this way. And when I run the Python interpreter, I should be able to import PyQGIS library and have it simply work. As you can see, I didn't get any errors, which means that the QGIS library is available. Rather than typing everything into the Python interpreter, we're going to create a Python source file to hold our work. Here we are. We're going to write our program in here and then run it using our terminal window once it's done. We start by importing the PyQGIS library. Now, because PyQGIS is built on top of the PyQt library, we're going to need to use the same library. Fortunately, PyQt is built into QGIS, so we don't need to download or install it. All we need to do is import the various libraries we'll need. Here we go. And another import statement here. Okay. We next need to create a Q application object, which represents our running application. Now that we have an application object, we next need to tell PyQGIS where to find the various files it needs. These files are stored as part of QGIS itself, and we can use the QGIS prefix environment variable we set up earlier to tell PyQGIS where to find its files. Our next step is to initialize the PyQGIS library itself. Now there's one more thing we need to do before we have a complete PyQGIS-based application. When our application exits, we have to tell PyQGIS to clean up after itself. Now this is actually a complete PyQGIS-based application, but it doesn't do anything yet. Let's change our application so that it displays a map. To do this, we're going to create a custom class called Map Viewer. Showing this map viewer is actually pretty easy. Here's our map viewer object we've just created. Now let's show it. And finally we're going to go, this last line tells QGIS to start up the application and keep running until the user quits. As you can see, we've passed in the name of the shapefile that we want to display. I'm using the World Borders dataset that we downloaded earlier. So now that we've got this, we next need to create the map viewer class itself. So here we go. Now, we're only going to need one method here, init, which, as you can see, we start by initializing the window, setting the window's title. Now that the window has been initialized, we next want to set up a map canvas to display the map. Next, we'll load in the shapefile as a vector layer. Then we're going to add our new layer to the map, set the extent so that the contents of the shapefile are visible, and tell Canvas to show the layer. And finally, we need to add our canvas to the window. This completes our map viewer. So let's try running it. Here we go. It's still very basic. You can't scroll or zoom the map, and the window shows white space above and below the image. But as you can see, we've created a simple standalone application using Python built on top of the PyQGIS library. Well done! In this video, we saw how you can create your own standalone Python programs that use the PyQGIS library. We saw how you can set up the Python path and various environment variables to allow Python to access QGIS, how to structure a PyQGIS-based application, and how to create a simple map viewer using Python and QGIS. This completes the first section of this video course. In this section, we started by looking at the QGIS application and how it works as a standalone GIS system. We then saw that there are 3 ways in which Python can be used with QGIS: by typing commands into the QGIS Python console, by creating Python plugins for QGIS, and by accessing the QGIS Python APIs from a standalone Python program. In the next section, we will look at the QGIS Python console in depth to see how it can be used to explore the QGIS system, run Python programs within QGIS, and customize the way the QGIS system works. Hello and welcome to this section is called the QGIS Python console. In this section, we will look at the Python console window in much more detail. We will learn about the various things you can do using the console, see how to work with geospatial data within the console window, and discover various ways you can customize the QGIS user interface using Python scripts. We'll now start with the first video in this section, entitled Using the Console. In this video, we will learn about the various parts of the console window, see how to enter Python statements and commands interactively, learn about the Python source code editor built into the console, see how to run scripts within the console, and learn how to dock and undock the console window. Now let's open the console window. As you can see, the console has three main parts: a set of toolbar icons along the top, the interpreter log in the main part of the window here, and at the bottom, an input field where you can type in various Python commands. For example, hi. As you can see, whenever you type a Python statement into the input field and press the return key, that statement will appear in the interpreter log, along with any output from the Python interpreter. Now let's have a look at some of the more important toolbar buttons. Firstly, there's the broom, where you can sweep away the previous contents of the log. This import class drop-down here lets you quickly select one of the import statements that you might want to use, one of the more common import statements you might want to use. And also over here is the options button, which lets you configure the way the console window works. And then there's the editor button, which we'll take a look at in a moment. Now let's take a look at some of the great things you can do when entering Python commands. First off, you can use the up and down arrows to select commands you typed previously. Here I'm pressing the up key, as you can see, going up through the various commands I've typed in before. Down lets me go back down through the list. And once I've selected a command I want to run, I can simply press return and it will be executed just like as if I typed it. Now, the input field also supports auto-completion, automatically showing you possible matches against the PyQGIS APIs as you type. Or, as you can see here, it's starting to select things. And if I go QGIS vector, it's selected. Now it makes it easier to type in the various classes. And if I have a look here, it'll actually show me all the different methods, constants, and types that are defined by this class, making it very easy to select various things. Now I'm going to try typing in a statement like 10 minus. As you can see here, the console automatically completes parentheses as you type, making it easier to type your statements. Also, if I type from something, it automatically inserts the import statement for me, saving me from typing. And finally, if I type something like, typing in a class name here, it puts in here, shows me in here the various parameters I need to supply to the initializer. And you see how the current parameter is highlighted in blue. So as I type, and type a comma, now it tells me I'm ready to do the second parameter here. Now if you don't like this behavior, this auto-completion behavior, you can turn it off in the options here, just like you can turn off the parentheses insertion and the import insertion. Now, while typing commands one at a time into the Python console does work, it quickly gets tedious. So instead, you can use the built-in editor to enter and run your Python scripts. Let's have a look at that now. Here's the editor. As you can see, the console window has been split in half, and the editor now takes over the right-hand side of the window. And once again, there are various toolbar icons at the top, as well as an area for typing in your Python code. So let's type in a simple Python program here. Here we are. As you can probably guess, this program prints out the name of each layer in the current project. Before we can run it, we have to save the script. So we're going to click on the Save button here, and I'm going to save it to example.py. For that. Now that the script has been saved, I'm able to run it by clicking on the Run Script toolbar icon, or alternatively I can use the keyboard shortcut, which is Command-Shift-E on a Mac or Control-Shift-E on a Windows or Linux machine. So let's try doing this. Here we are. See over here on the interpreter output that it's run my program. This first statement here, exec file, that's a Python built-in command to execute the contents of a script. And as you can see, it's running my example.py file. And the remaining file lines here are the output from my program. Now in this case, I had loaded a project in beforehand so that we'd have some layers to display. Now while there are no keyboard shortcuts for the open, save and save as command toolbar icons, by default QGIS will automatically save your script before you run it, so you don't need to use the toolbar icon. You can make a change and then run it using Command-Shift-E. Note that you can use this built-in edit and run any Python script. It's quite a useful way of running Python code within the QGIS environment itself. One of the most amazing things about QGIS is how configurable the user interface is. For example, I could take the console window and dock it so that it becomes part of the main window. To do this, click on the title of the console window and drag it down into the main window. And when I release the mouse button, you can see it now becomes part of the main window. This is very powerful, though it can be a bit confusing. And it's quite useful to know about this before we start. Well, the other thing you can do is you can double click on the title to dock or undock the window. Now that doesn't just apply to the console window, it applies to all the parts of the window, so I could now undock the layer. That can be a bit confusing, this docking behavior, so it's quite good to know about it before you accidentally dock your console window. In this video, we learned about the main parts of the console window. We saw how you can use various shortcuts for entering Python code, and how you can use the built-in editor to enter and run any Python script within the QGIS environment. Finally, we saw how the console window can be docked into the main QGIS window and how to undock it again if you do this by accident. This completes our look at the QGIS console itself. In the next video, we will use the console to write a Python script which loads data into QGIS from a shapefile and then performs some more complex calculations using that data. Hi there! In the previous video, we looked at the QGIS Python console and how it can be used to run Python code interactively, as well as for writing and running Python scripts. In this video, we will use the QGIS Python console to learn more about the PyQGIS library. We'll use it to access geospatial data sources, to calculate real-world distances and areas, and to deal with the structure of often complicated geometries. All of this will be used to create a script that analyzes the contents of a shapefile. Let's create our script. We're going to use the built-in script editor in the QGIS console, and we'll save it to the desktop. I'm going to call it Analyze Shapefile. Here we are. Now, we're going to start by importing some classes that we need. In order to make our program a bit easier to work with, we'll actually put all of the code into a function, and then we're going to call that function when our program is run. Rather than hardwiring the name of the shapefile, let's use QGIS's built-in file selector to let the user choose the file to analyze. So I'm just inserting the text to make it a bit quicker. In a previous video, we used the iFace variable to add a vector layer to the project and then access the contents of that layer's data source. That's fine if you want to create a project, but in our program we just want to access the data. To do that, we're going to use a data provider to open the shapefile directly. Here we have it, a data provider. As you can see, we have to abandon ship if the user didn't select a valid shapefile. Later on, we're going to need to have a list of the various attributes defined for this shapefile. So let's grab that information now. Iterate over the various fields defined for the shapefile and extract the field name and store it into a list. Because of the way map projections work, we can't simply calculate the length of a line or the area of a polygon when that polygon or line are positioned on the surface of the Earth. For example, if we try to calculate the length of this blue line here, we'd end up with a totally meaningless number because the computer would just naively calculate the geometric length of the various points, the geometric distance between the various points that make up the line. And because they're in latitude and longitude values, we'd end up with a line length of 3, which is kind of meaningless given that this line is actually about as long as the distance between New York and Philadelphia. What we need to do is calculate the distances and areas using real-world units such as miles or kilometers. To do this, we have to use a special QGIS class called QGIS distance area, which calculates distance areas in meters. Let's set one of these up now. Now there are a few things you need to do to use a QGIS distance area calculator, but it's not actually all that hard. Go there. Now, as you can see, there's a few options for you to set up, and you can look up the documentation if you want to know what these all are, but that's not that bad to actually do. Now, because we want to calculate the total length and area for the entire shapefile, we're going to need some variables to store these totals as we calculate them. So let's just put them in there now. Now, we're ready at last to start the main part of our program. Let's start by scanning through the contents of the shapefile, one feature at a time. Okay. Now for each of these features, we're going to want to find a suitable label to use to describe that feature. We're going to look for an attribute called name and fall back to using the feature's ID if there's no name attribute in the shapefile. As you can see, the attribute names are case sensitive, so we have to check for each possible version of the name attribute. We now want to calculate the length of each line feature and the area of each polygon feature. Before we can do that, we have to get the feature's geometry. We now use that to identify the type of geometry we have. Okay, here we are. Now, for line geometries, we're going to calculate the length of the line. Now, this time, because the QGIS distance area calculator returns a length in meters, we have to divide that number by 1,000 to get the length in kilometers. Now let's do the same thing for polygons. This time we want to calculate the area. I'm going to calculate it in square kilometers. Here we are. And because it's returning a value in square meters, we have to divide by 1,000,000 to convert it to square kilometers. Finally, for other types of geometries, we're simply going to display the geometry's type. Now that we've done all these calculations, let's display the results, printing out the label and the feature and the information we calculated for each of those features. And finally, we just want to display the total length and area for all of the features in the shapefile. Here we are. Now this completes our program, so let's try it out. Save it and try running it. Now it's asking us for the name of a shapefile, so let's select the world borders dataset, and there we go. As you can see over here on the left, it's displaying all of the information that it's calculated. As you can see, it's quite possible to create Python programs that read and analyze geospatial data, and you can run these programs directly within the QGIS console. It's also possible to create and manipulate geospatial data sources using the PyQGIS libraries. In this video, we created a program which directly reads the contents of a shapefile, calculates the length and area of the shapefile's features, and displays the results on the screen. In the next video, we will learn about the various ways we can use Python scripts to manipulate the QGIS user interface. Hello there! Welcome to this video titled Scripting the QGIS User Interface. In the previous video, we wrote a Python program which analyzes the contents of a shapefile. In this video, we're going to look at various ways you can incorporate user interface elements into your QGIS Python programs. We'll see how to interact with the QGIS status bar, how to display messages in the QGIS message bar, and how to use progress indicators. We'll learn how to write messages to the QGIS logging panel and finish by creating a custom dialog that lets the user supply information for your program to use. The QGIS window has a status bar which you can use to display the current status of your Python program. Let's set a status message. Now when we run this, as you can see down here in the bottom corner, here's the status message we've just set. Now you can use this whenever you want to display a short message to the user while your program is running. If you want to erase the status message, you can use the clear message method, like this. And as you can see, the status message goes away. The QGIS message bar is used to show temporary messages at the top of the window. Let's use this to display a simple message. As you can see up here, here's the message that we displayed. As the name suggests, push message is used to create a stack of messages. So that if I, for example, created a second message here, it would go on top of the existing message, and it tells me that there's more than one status message to be displayed. And if I close the second message, the first message is shown. Now you can do lots of fancy things with the message bar. For example, you could include a level which affects how the message is coloured, or you could add a title to the message, or even set a duration after which the message is automatically hidden. Let's try some of this. We're going to go iFace, message bar, push message, title and a message. We're going to set the level, critical message, and we'll set a duration. Now you can see the messages in red here. Had a title and disappeared after 4 seconds. Finally, you can clear all of the messages which are currently showing using message bar .clear widgets, and the message bar goes away. Now let's use the message bar to create a progress indicator. To do this, we'll create a custom message, add a Qt progress bar control to the message, and then display it. We'll start by creating the message itself. I have a message in there, don't I? Here we go. Now to create the progress bar, we'll have to import the Qt library. So here we go. Fingers are misbehaving. And we also need to import from Qt core. Right. We're now ready to create the progress bar itself. And now we can add the progress bar to our message. And finally, we can push the message onto the message bar. And here we have it. You can see we now have a progress indicator on the top of the window here. Now, let's try setting the value of our progress indicator. By default, it goes from 0 to 100, so 20 is 20% of the way there. And likewise, we can keep updating it as we update our program. Our program does whatever it needs to be doing. And finally, we can remove the progress bar again just by going clear widgets. QGIS also has a built-in logging system. Have a look at by going down to panels and log messages panel. Here it is. Now it's easy to add new messages to the QGIS log. Let's do that here. As you can see, we now have a hello message added to the log. We can also change the importance of the message by adding a level. For example, as you can see, the level here that's just displayed as a number has changed. Now, if you want to, you can also tag your messages so that they appear in a completely separate tab within the log window. Let's see how that works. Now we have a new tab here called My Log, which just contains the messages that I created. Because QGIS is built on top of Qt, you can use all of Qt's user interface classes to create your own windows and dialogues and display them directly within your Python code. To see how this works, let's write a script that creates a custom dialog box which prompts the user to enter a latitude and longitude value. We'll use the built-in editor here. A bit bigger. Now, here we go. First of all, we're going to save our file. Call this dialog.py. And I need to do one of those import statements again. Now, our custom dialog box is going to be a subclass of QDialog. We're going to need to create an initialization function, standard Python initializer. Now we're going to start by initializing our dialog and setting the Windows title. We next need to create what's called a form layout object to lay out the various parts of our dialog box. Here we go. We'll create a label and input field for the latitude and another one for the longitude. Next we want to create a push button object for the OK button and another one for the cancel button. Here we are. So Q push button, OK accepts the dialog, and cancel will reject it. Pretty standard behavior. Now that we've defined all the various parts, let's lay out the buttons side by side in the window using a horizontal box layout object. This lays the buttons side by side. We can then add all the various parts to the form layout we created earlier, adding the latitude label and field, the longitude label and field, and then our buttons. As we'll place those things one above the other. Finally, we can tell our dialog to use the form layout that we've created. This completes our My Dialog class. So let's write some code now to use this dialog to display it on the screen. So here we go. First thing we do is create the dialog and then execute it. If the user clicks on the OK button, we're going to want to grab the latitude and longitude values that the user entered. Now, for our simple example program, I'm just going to print those values out. So there's a very simple Python program. Now let's try running it and see what happens. Here we are. You can see our dialog box has popped up and it's asked us for some values. So let's say a latitude of 36 and a longitude of 101. And when I click on OK, look, it prints it out in the console just like we expect. So as you can see, it's quite possible to create custom dialogues and windows that interact with the user, and you can include all of this code directly in your Python programs. This is the last video in this section. In this section, we learned how to use the QGIS Python console in much more detail. We used the built-in editor to write a Python program which reads and analyzes the contents of a shapefile, and then looked at various ways in which Python programs can interact with the QGIS user interface. Coming up next, we have Understanding the PyQGIS library. Welcome to section titled Understanding the PyQGIS library. In this section, we will look at the PyQGIS library in much more depth so you can understand how it is organized and how to use it. We're going to focus on two particular packages within the PyQGIS library. The QGIS.core package, which implements core functionality used throughout the QGIS system, and the QGIS.GUI package, which implements a range of GUI widgets that make up the QGIS user interface. We'll now start with the first video in this section, which gives an introduction to the PyQGIS API itself. In this video, we will see how your Python code is able to access the C++ based QGIS APIs. We'll learn enough about C++ to read and understand the C++ oriented documentation and see how these APIs are organized. The QGIS system, including the QGIS APIs that we've been using, are all written in C++. In order to access the C++ based code from Python, we have to use various wrappers around the C++ code. For example, when we call the QGIS geometry.area method here from our Python program, the Python interpreter calls a specially generated wrapper function written in C++. This then calls the QGIS API function, which does the actual work here. Fortunately, these wrapper functions have been very cleverly written, and in most cases you don't need to worry about the fact that the underlying code is written in C++. However, there are some situations where your program can mysteriously crash if you don't know what's happening. For example, when you try to refer to an object that the C++ code has already deleted. We'll look at these issues in more detail later when we get to them. The fact that the QGIS APIs are all written in C++ makes life a bit more difficult for us Python programmers. All of the documentation for the APIs is written in C++. Let's take a look at this documentation. Here's the computer-generated documentation for the QGIS APIs. Different classes that are available. Now, let's have a look at the QGIS interface class here. This implements the iFace variable that we saw earlier. Now, if we look down here, you'll see that there are well over 100 different methods defined for the QGIS interface class. It can get pretty confusing. Let's go down here. Have a look at this method here, zoom to active layer. Now, this is the definition for this method. As you can see, the documentation here is for C++ and includes some things that can be pretty confusing for Python programmers. First, there's the virtual keyword here, which fortunately we can ignore. Next, we have void. Now, this void is C++'s way of telling you that the method does not return a value. Now then, following this, we have the method name itself, which is QGIS interface : zoom to active layer. Double colons here are C++'s convention for separating the class name from the method name. And finally here we have the parentheses. And just like in Python, it shows us that this particular method does not take any parameters because parameters are put in between the parentheses. Now let's have a look at a slightly more complicated example. Here we go. This method here. Add vector layer. Now what on earth is all this lot here? Well, for starters, we have here this line here, QGIS vector layer star. This replaces the void that we saw earlier. It tells us what type of information is being returned by the method. In this case, it's returning a pointer to a QGIS vector layer object. We next have three parameters here. And as you can see, they're given a name and a type. In this case, QString, which is the type of parameter. Because C++ is strongly typed, every parameter has to be given a type definition. So even though the description here is very terse, we can actually discover quite a lot about this method just by looking at what information it returns and what parameters it takes, and also the name of all the parameters. Now you shouldn't have too much trouble figuring out the various parameter types. There's int, long, float, and bool, which are all pretty obvious, QString, which is a string, and a QList object, which is a list. And then there are the various class types defined by QGIS itself, QGIS vector layer and the like. Now just like in Python, parameters can have default values. If you look at add raster layer, you can see here that in this case, the base name parameter is given a default value of an empty string. Now in Python, objects are initialized using the init method. In C++, these methods are called constructors. Here we'll have a look at constructor for this particular class. As you can see, the constructor is simply a method that's named after the class itself, so QGIS interface : QGIS interface. So this is the constructor, the initializer for the method. Just like in Python, C++ classes inherit the methods defined by their superclass. If you're looking for a method and can't find it, check in the superclass to see if it's defined there. Now there's one more thing you need to know about C++, which is the concept of method overloading. Python doesn't have this, and it can be pretty confusing if you don't know about it. In C++, you can define the same method multiple times, where each implementation of the method accepts a different set of parameters. If we look at the address layer, we have two different methods that are both named address layer. Because there are different sets of parameters, however, the C++ compiler can figure out which version of this method to use based on the parameters that were supplied. Hopefully you can see that it's not too hard to decipher the documentation for the QGIS APIs, even though the documentation has been written for C++. It doesn't actually take long for your brain to start filtering out the C++ gobbledygook, and you'll be able to use this reference documentation as you write your PyQGIS-based Python programs. Let's now see how the QGIS library has been structured. All of the PyQGIS libraries are organized under a single package called QGIS. You don't normally import the QGIS package itself, however. Instead, you import one or more sub-packages, and there are 5 sub-packages that you might be interested in. Firstly, QGIS.core defines the core GIS functionality used throughout the QGIS system. Next, the QGIS GUI package implements a range of GUI widgets which you can use in your own program. The QGIS.network analysis package provides various tools for analyzing topological networks. The QGIS.analysis package implements spatial analysis tools for analyzing vector and raster format data. And finally, the QGIS.utils package provides various miscellaneous functions that allow you to work with QGIS applications using Python. In this video, we saw how Python programs are able to access the C++ based QGIS APIs, learned how to decipher the C++ oriented documentation for the QGIS APIs, and saw how these APIs are organized. In the next video, we will take a closer look at the QGIS.core package, learning about many of the important classes which you will need to use when writing Python programs that use the PyQGIS API. In the previous video, we started our examination of the PyQGIS library by seeing how the C++ library is accessed from Python, learning how to read the C++ oriented documentation, and seeing how the library is structured into separate sub-packages within the main QGIS package. In this video, we will look in more detail at the QGIS.core package. We will see the different types of map layers which can be used to create a map, learn about coordinate reference systems, and see how you can display and manipulate vector-based geospatial data. We'll then see how the QGIS.core package lets us display and manipulate raster format data before looking at a few other QGIS.core classes that you may want to use. When you use QGIS to generate a map, that map is made up of various map layers. In this example, we have a raster base map layer with river and lake map layers drawn on top to build the generated map. There are 3 types of map layers you can use for drawing layers onto a map. A vector layer, which draws geospatial features such as points, lines, and polygons. A raster layer, which draws raster format or bitmapped data directly into a map. And a plugin layer, which lets you use a plugin to draw onto a map. Notice that each of these map layers has a corresponding class within the QGIS.core package. There's also an abstract map layer class, QGIS.core.QGISMapLayer, which represents a map layer of any type and acts as the common superclass for these 3 types of map layers. Before we can use these map layers to display information, we need to learn how geospatial data is positioned onto a map. And this brings us to the concept of a coordinate reference system. The Earth is, roughly speaking, an oblate spheroid, while a map is a flat Cartesian plane. A coordinate reference system, or CRS, is a way of converting between these two. A CRS will allow you to take a point on the Earth's surface and calculate the equivalent point on a map, or vice versa. Now there's a lot of very complicated maths around how coordinate reference systems work. It's mathematically impossible to have a perfect CRS. One CRS might distort the position of objects, while another might distort distances between objects. Some CRSs work well in certain areas of the world, while being very inaccurate elsewhere. There are hundreds of different coordinate reference systems available, all of them suited for a particular purpose and none of them perfect. In terms of geospatial development, you need to know which CRS a given set of geospatial data is using and tell QGIS to use the right one. Fortunately, QGIS comes preloaded with a big database of all the standard coordinate reference systems. QGIS Coordinate Reference System class represents a CRS. Let's create an instance of this class. Now 4326 is an EPSG code for a very common CRS used by GPS satellites. This CRS places geospatial data onto the Earth's surface using latitude and longitude values and also uses a standard mathematical model of the Earth. A lot of geospatial data uses EPSG 4326, and this is actually the default CRS used by QGIS. Once we've created a CRS object, it's easy to tell a map layer to use it. There we go. Let's now have a look at how vector format data can be displayed and used within QGIS. As you should already know, geospatial data is stored externally to QGIS itself in a vector data source. A data provider then allows you to access that data source and makes it available to the QGIS system as well as your Python code. Finally, a vector map layer is used to include that vector format data as part of a map. Let's have a closer look at each of these. A vector data source consists of a number of features, where each feature is like a record within the data source. Each feature, an instance of QGIS.core.QGIS feature, has a unique ID, a geometry which stores the point, line or polygon for this feature, and a list of attributes which contains information about the feature. A vector data provider, which is an instance of the QGIS.core.QGIS vector data provider class, includes a reference to the data source, a geometry type which tells you what type of geometry data is stored in the data source, and a list of fields which tell you which attributes are available. The vector data provider also includes functionality to let you search for and retrieve the features within the data source. Finally, a vector map layer, which is an instance of QGIS.core.QGIS vector map layer, is used to display vector data on a map. Each vector map layer object has a data provider, a coordinate reference system, and a renderer. Now the renderer tells QGIS how the vector features should be displayed. Let's take a closer look at this notion of a renderer. There are two related concepts here, a symbol and a renderer. The symbol tells QGIS how to draw a given point, line or polygon, while the renderer chooses which symbol should be used for a given feature. In the simplest case, every feature is drawn using a single symbol. This is done using the single symbol renderer, which is represented by the QGIS.core.QGIS single symbol renderer v2 class. Now don't worry about this v2 business here. That's just there to maintain backward compatibility with some old code. The next type of renderer we have, the categorized symbol renderer, can assign specific symbols to specific attribute values. You can imagine how this could be useful, drawing different roads, for example, in different ways. Now the final type of renderer, the graduated symbol renderer, assigns symbols based on ranges of attribute values. Now there are three main types of symbols that you might be interested in. The marker symbol displays a point as a filled circle, the line symbol draws a line using a given width and color, and the fill symbol draws the interior of a polygon. Internally, symbols can get quite complicated, using layers to draw elements one on top of the other. To make things easier, PyQGIS lets us create a simple version of a symbol. This creates a single layered symbol. Let's see how this works. Now we've already got a reference to our river layer in the variable called layer, so let's change this layer to display the rivers in a different color. QGIS single symbol renderer v2. Once we set up a renderer, we tell the layer to use it. Typo there, sorry about that. And then finally we can tell QGIS to redraw itself. And as you can see, we now have our rivers drawn in red. As well as displaying a vector data source, you can also retrieve its contents. Let's scan through the river data source. We'll start by getting the data provider for our map layer. We next need to create a QGIS feature request object. This lets us retrieve the features from the data source. You can add filter expressions to retrieve only certain features, but by default a feature request will return everything. We can use this request object to iterate over all the features. Once we have the QGIS feature object, it's easy to get the geometry, the ID, and some attributes. In this case we'll get the name attribute. For now we're just going to print these out. And here we go. Now the geometry object is an instance of QGIS.core.QGIS geometry. And this has a ton of methods you can use to analyze and manipulate the geometry if you want to. Let's take a quick look at raster data. In many ways, raster format data works in the same way as vector data. There's a data source, a data provider, and a map layer. Raster data uses a single pixel or cell to represent part of the Earth's surface. A raster data source often has multiple bands to store different pieces of information. Rather than a CRS, which applies to vector format data, a raster provider uses what's called a georeferencing transform to map individual cells within the raster to areas on the Earth's surface. When displaying raster data on a map, the raster layer converts each cell into a different color. There are different ways in which this can be done. The main ones are grayscale, where each cell directly corresponds to how light or dark the cell will be drawn, multi-band, where different bands in the cell will be used for each component of the color, and paletted, where a color palette is used to select the color for each raster value. Just like with vector data, it's possible to access the underlying raster data using the data provider. You can do this for an individual cell, done here, or you can retrieve a large number of cells at once using the provider.block method. Here's some example code that shows you how this can be done. Finally, let's take a look at some of the other QGIS.core classes which you might find useful. First, we have QGIS project, which represents the current QGIS project. Next, we have the QGIS class. This is kind of a utility class defining various constants, data types, and functions which you might find useful. We next have QGIS point and QGIS rectangle, which are objects representing points and rectangles. The QGIS distance area class is a very useful class for calculating real-world distances and areas. Finally, the QGIS map layer registry class lets you access all of the map layers within the current project. In this video, we looked in detail at the QGIS.core package within the PyQGIS library. We saw that there are 3 types of map layers, learned how coordinate reference systems work, and discovered the various classes for working with vector and raster format data. We also looked briefly at some of the other important classes in the QGIS.core package. In the next video, we will turn our attention to the QGIS.GUI package, which defines a range of user interface elements which you will want to use in your own programming. Hello again. Welcome to video Important GUI classes. In the previous video, we looked in detail at the QGIS.core package. In this video, we're going to turn our attention to the QGIS.GUI package. We'll learn more about the QGIS interface class that we've accessed using the iFace variable. We'll learn about the map canvas and how we can add items to it. We'll see how map tools work and look at some of the other classes in the QGIS.GUI package which you may find useful. Let's start by looking at the QGIS interface class. We used this class earlier. It's available using the iFace variable in the QGIS console and is also made available to plugins. Note that the QGIS interface object is only available when you're running the QGIS application itself. If you write a standalone Python program and import the PyQGIS APIs, then the QGIS interface object won't be available. Let's look at some of the interesting things that we can do with this class. Firstly, we can use the legend interface method to get a list of all the map layers which have been added to the map's legend. We can use iFace.mapCanvas to get a reference to the map canvas displayed within the main application window. We can get the currently selected map layer by calling iFace.activeLayer. We can also select a different map layer by calling iFace.setActiveLayer. If we want, we can get a reference to the application's main window. This can be useful if you want to create additional Qt windows or dialogues which use the main window as their parent. And finally, we can get access to the QGIS message bar by calling iFace.messageBar. This lets you display messages directly within the QGIS main window. Let's now turn our attention to the QGIS.core.QGIS map canvas class. This represents a map canvas, and as you can see, it's used to draw the main part of the QGIS window. We can also use it in our own standalone programs. Let's have a look at some of the things you can do with the map canvas. The layers method returns a list of the currently visible map layers. Note that if a map layer is hidden, it won't appear in this list. The extent is the part of the world currently shown by the map canvas. As the user pans and zooms the map, the extent will change. Note this is always going to be a rectangle. You can use the extent method here to retrieve the current extent and the setExtent method to change it. Now, a map tool is an object that lets the user interact with and manipulate the contents of the map canvas. The map tool method here lets you retrieve the current map tool, and the setMap tool method lets you switch to a different map tool. We'll look at map tools in more detail shortly. Finally, the canvas color method is used to set the background color used to draw the canvas before the map layers are drawn. This can be used to set a background which appears behind the map layers. Let's now take a look at map canvas items. A map canvas item is an item drawn on top of the map canvas, in front of all the map layers. There are three subclasses of QGIS map canvas item that you might be interested in, though you can also create your own if you want. The QGIS vertex marker class draws an item such as a small X centered around a given point on the map, and this is often used to highlight vertices or mark specific points. The QGIS rubber band class draws an arbitrary line or polygon. It's intended to give feedback as the user draws a new line or polygon onto the map. The QGIS annotation item class is used to display information in the form of a balloon that is connected to a given point in the map. There are various subclasses of QGIS annotation item available, allowing you to customize the way information is displayed. The QGIS map tool class represents a map tool. Map tools let the user interact with and manipulate the map canvas and its contents by capturing mouse events and responding accordingly. Much of QGIS's standard behavior is implemented using map tools. Let's take a look at some of the more common map tools you might like to use in your own programs. Firstly, there's QGIS map tool pan. This lets the user pan the map, that is, click and drag the map to move around. Similarly, QGIS map tool zoom is used to zoom in or out when the user clicks on the map. QGIS map tool identify lets the user point to something and click, and the map tool will identify the clicked on raster cell or vector feature. Finally, the QGIS map tool emit point class is intended to be used as the starting point for other custom map tools. When the user clicks on the map, the canvas clicked method is called with the coordinate the user clicked on. You can use this in your subclass to respond in whatever way you want when the user clicks on the map. Let's finish this exploration of the QGIS.GUI package by looking at some of the other classes which you might find useful. The QGIS map tip class represents a tooltip that gets displayed when the user hovers the mouse over a feature. The map tip will display a particular attribute value for that feature, and you can choose the attribute by calling the layer.setDisplayField method. The QGIS dialog class is a generic dialog with a standard layout and space for buttons at the bottom. This helper class makes it easy to add contents and buttons so you can quickly display a dialog to the user. The QGIS color dialog is a color selector. When you display it, the user is asked to choose a color, which is then passed back to your program. The QGIS message bar displays non-blocking messages to the user right within the main QGIS window itself. And finally, the QGIS message viewer class makes it easy to display long messages within a modal dialog. In this video, we looked at the QGIS.core package, examining many of the important classes which you will need to use in your QGIS-based programs. This finishes the current section. In this section, we saw how the QGIS Python APIs are organized, learned how to decipher the C++-based documentation for QGIS, and learned about many of the important classes within the QGIS.core and QGIS.GUI packages. In the next section, we will use what we've learned to solve a range of real-world geospatial programming challenges using the PyQGIS library. Hello, and welcome to the section Using the PyQGIS library. In the previous section, we took a detailed look at the PyQGIS library, how it is organized, and some of the more important classes it defines. In this section, we will apply what we have learned to solve a number of real-world geospatial programming challenges. We'll see how to work with raster format elevation data, learn how to manipulate and save vector format data, discover how to use different symbols for different features within a map, and calculate the distance in meters between two user-defined points. In this first video, we will use PyQGIS to analyze some raster format elevation data. This will give you experience in working with raster format data using the PyQGIS library. In particular, we're going to find and download a DEM file or digital elevation model. We'll then learn how to use PyQGIS to read the contents of this file and use this to calculate a simple histogram of distinct elevation values. A digital elevation model or DEM file is a raster format data file containing elevation values. Let's download a DEM file so that we can have a play with it. Now we're going to use Google to look for something called Globe DEM. There it is there. Now we're going to get the download the data. We want to download a tile. DEM files are notoriously big, so we just want to download part of the world, not the whole world. We're looking for the Western United States, which as you can see is part of tile E. So let's download this tile, tile E. Now once this has been downloaded, we get a zip archive. We'll put that file on our desktop here, and let's expand it. As you can see, the archive contains just one file, E10G. Now this file contains all of the raw elevation data, but unfortunately by itself it isn't very useful because there's no way of knowing where on the Earth's surface this data should be placed. To georeference this data, we're going to need a header file, and that unfortunately isn't provided by the Globe website itself. Now there are various places where we can get this header file from. I'm just going to Google it to see if I can find it. There's one of the locations that's available. There it is there. Download linked file as, and I'm going to save it to my desktop. Now, Safari helpfully put a little txt suffix on the end of it because it is a text file, but we don't need that. There we go. They're the two files we need. Now that we've downloaded our DEM file, let's see how that we can. Now that we've downloaded our DEM file, Let's see how we can use PyQGIS to access it. We'll start by creating a Python script. QGIS console, here we are, and I'm just going to save this to my desktop and I'm going to call it readdem.py. We first have to create a data provider to access this file. To do this, we first have to get a registry of available data providers. We can then ask the registry to create a data provider for us. We're going to tell it that we want to use a thing called the GDAL library. GDAL is a standard library for reading and writing raster format geospatial data. Then we have to tell it where the file is. In this case it's on my desktop and it's called E10G. Now that we have a data provider, let's write some Python code to read through the contents of our DEM file. We're going to use the provider.block method. This method is going to need to know the area of the Earth's surface covered by this DEM, as well as the number of cells across and the number of cells down to read. Now we can get all of this information from the provider itself. We can now read the DEM's data into memory using the provider.block method. We're going to need to tell the block method which band to use, the extent, the width, and the height. In this example, we're reading all of the data from the raster file. Obviously, by changing the parameters, we could load only some of the data from the file if we wanted to. The block variable is going to be an object of type QGIS raster block, which is basically a two-dimensional array of values. Let's iterate over these values one at a time. Now that we've got our elevation data, there are all sorts of things that we could do with it. In this example, we're going to create a histogram. A histogram contains a count of the number of times each unique value occurs. Let's modify our program to generate a histogram. First of all, and down here, as you can see, we just have a dictionary mapping elevation values to the number of times the elevation value occurs. Now let's finish our program by printing out the histogram. Yeah. So let's save our program and try running it. Now there are about 65 million cells in this particular DEM file, so it does take quite a while to run. And it also takes a long time to print out the results because printing to the QGIS console is unfortunately quite slow. You're just going to have to be patient. So let's have a look up the top here. There's this value here of -500, and as you can see, it occurred millions and millions of times. What does -500 mean? Well, in this particular DEM file, the -500 value is a special value called the no data value. This represents the parts of the DEM dataset which are over the sea and so don't have any elevation. Now let's modify our program to ignore these values. First of all, we're going to have to go we want the no data value for band 1 here. And then down here, we're just going to say there. Now, if we ran our program again, it would now exclude the no data values, showing only elevations for those cells which are actually over the land. In this video, we use the example of a digital elevation model to learn how to read and analyze raster format geospatial data. In the next video, we will turn our attention to vector format geospatial data, learning how to read and write shapefiles and also how to subtract one set of polygons from another. In the previous video, we saw how to work with raster format geospatial data. In this video, we will turn our attention to working with vector format data. We'll use shapefiles and learn how to read vector format data from a shapefile into memory, how to manipulate vector format data, and how to save that data back into a shapefile again. Imagine that you have 3 hospitals in your local city. Each hospital is intended to take patients within a 10-kilometre radius. You want to know how much of the city is covered by these 3 hospitals. Now you might plot the location of each hospital and the area each one covers, like this. However, because your city is on the coast, you'll need to exclude the parts of each circle that sit over the water. To do this, you can subtract the ocean from each of your circles to get a polygon that includes the area of the city covered by each hospital. You can then measure the area of each polygon to see how much of the city is covered by each hospital. Now, there are lots of examples like this. This is just one that I made up. But let's write a program that solves this type of problem. Now, we're going to use a script to hold our work, and we'll save it here, and I'm going to call it subtract shapes.py. Now, let's start by importing the various library modules that we're going to need. And to make things easier, we're going to put all of our code inside a function. The first thing that a function will need to do is ask the user to select a shapefile. We'll use the QFileDialog class to do this. As you can see, the QFileDialog class takes 4 parameters: a reference to the parent window, a label, the directory to start searching from, and a filter to choose what type of file it wants. If the user cancels, we just return. You can see that's why we put everything in a function, make it easy to cancel out. Now that we have a file to work with, let's open up a vector data provider. Here we go. We'll load that data into memory. We next want to read the geometries from the shapefile into memory. Now, at this point, we want to add the features geometry into the geometries 1 list. Now, here's one way of doing this. All right. Unfortunately, you might think this would work. You might think you could just take the geometry and add it to a list. But if we did this, our program would actually crash. Now, this is one of those quirks of QGIS that we mentioned earlier when looking at the way the Python wrappers are implemented. The feature.geometry method returns a reference to the geometry, but it doesn't know what you're going to do with that geometry. By default, the C++ code will release the memory used by that geometry when the feature goes out of scope. If you try and add a reference to that geometry to a list, like we're doing here, we'll be referring to the geometry after the memory it uses has been released, and our program will promptly crash. So to avoid this crash, let's replace this with the following. So we have to create a new geometry object that is a copy of the geometry from the feature. Now we've now loaded all of the geometries from the first shapefile. Going back to our hospital example, these geometries would correspond to the circular areas surrounding each hospital. We now need to do the same thing with a second shapefile. The second shapefile would correspond to the area of the ocean in our example. Now our next task is to subtract the second set of geometries from the first. Let's think about what this means. We can have multiple features in each shapefile. For each feature in the first shapefile, we want to subtract any features from the second shapefile which happen to overlap that feature, like this. While we could go through each feature in the second shapefile and see if it overlaps a given feature in the first, that wouldn't be very efficient. Instead, what we can do is combine all of the features in the second shapefile into a single multi-polygon geometry, and then just subtract that geometry from each feature in the first shapefile. Let's see how to do this. First, we want to create a combined geometry. Now the combine method here is adds the geometry to the combined geometry by using a geometrical union operation. After running through this loop, the combined geometry object will contain all of the geometries from the second shapefile. We can now calculate a new set of geometries by subtracting the combined geometry from each feature in the first geometry in turn. Now there are a couple of things to be aware of. Firstly, the resulting geometry might be mathematically invalid. Unfortunately, geometries are a mathematical concept, and it's not at all uncommon to get geometries which are mathematically invalid as the result of an operation like this. There are various ways of fixing this, but we're not going to worry about that now. Instead, we'll simply ignore any geometries which are invalid. Now, the second thing that might happen is that the geometry might be empty. If a feature in the first shapefile is completely overlapped by a feature in the second, then there won't be anything left after we subtract the geometries. Let's handle this case too. Finally, we can add this new geometry to our list of destination geometries. Now that we've done all of our calculations, let's save the results back into a shapefile again. We'll start by asking the user to choose the destination shapefile. Now we're going to make use of something called a vector file writer to save the subtracted geometries to disk. Here's how we set up a vector file writer for a shapefile. Note to editor, it would be good if you could edit out those little insert things where I don't type correctly. Going on. Notice that we create a fields object, which is an instance of QGIS fields. But we don't actually define any fields. That's because our output shapefile won't have any attributes. Now that the file writer has been set up, we can use it to save the selected geometries to disk. Like that. This is all very straightforward. Finally, we'll delete the file writer output to close the output file, and we'll display a nice message so the user knows that we're done. Yeah, see? Now this completes our program. Let's try it out. Save it and run it. And it's asking us to choose the first shapefile. Now I've already got a shapefile set up that contains all of the lakes in the United States. Let's subtract these lakes from the outline of the USA. So I'll use the world borders data set as the first shapefile, and then the second one, my US lakes shapefile. Now, it does take a few seconds to combine all of the lakes and then subtract them from each country in turn. And now it's asking me to choose the output shapefile. So let's save it to a file. I'll call it temp.shp, and I'll just stick it on my desktop. Subtracted feature saved to disk. Okay, so let's have a look at the results. We're going to go here. I just want to look at the temp.shp file. There we are. Now, if I zoom in a bit on the northern United States, we can already see that there are lots of holes in the United States now caused by all the lakes. And just show, you can see that we've successfully subtracted the lakes from the United States outline. And this shows that our program is working as it should. In this video, we saw how to read data from a shapefile, how to manipulate geospatial data using the geometry objects methods, and how to save that data back into a shapefile again. In the next video, we'll write a program that displays a map using different colors for different features based on the value of an attribute. In the previous video, we learned how to load, manipulate, and save vector format data using the QGIS API. In this video, we will write a Python program that creates a map layer and then modify that map layer so that different features are colored in different ways. We'll use a categorized symbol renderer to select colors based on distinct attribute values, and then use a graduated symbol renderer to choose colors based on ranges of attribute values. This will show you the two main ways in which you can color your maps. Let's create a script to hold our code. I'm going to save it to the desktop, and I'm going to call it renderers.py. Here we are. Now, a script will load the world borders dataset into a map layer, which we will call countries. Because we want to be able to run our script multiple times, the first thing we need to do is remove any map layers called countries so that we don't get multiple copies of this layer in our project. Here's how we can do this. As you can see, we use the QGIS map layer registry to get a list of all the map layers named countries, and then we remove them. Now we can add the world borders dataset as a map layer. Let's add a vector layer. We're going to want to use the data source's attributes to choose how to color each feature. So let's have a look at these attributes. First, let's get a list of the attributes which are available. See what happens. Here we go. So as you can see, we've loaded the map layer into the project, and it's now printing out a list of all the attributes. Now, there are two of these attributes that are going to be of interest to us. First of all, the POP 2005, which gives us a population value for each country, and the region, which gives us an ISO region code for each of the countries. Now this map's pretty ugly at the moment, so let's use that region code to color the map. Get rid of what we just created there. What we're going to need to do is set up a list of categories, one for each distinct region value. For each category, we're going to need to know the region code, the color to use, and a label for the category. We're going to set up a symbol to use the category's color. See, we ask the layer for the type of geometry it has, then we create a symbol for that type of geometry, and then set the symbol color to the desired color. We then create what's called a QGIS renderer category object to use the symbol for that particular region value. Now that we've set up our categories, we can tell the map layer to use a categorized symbol renderer object to choose the symbol based on the value of the region attribute. Categorized symbol renderer using the region for those categories. And finally, we can force the mapped layer to redraw itself so that we can see the results. Here we are. Now let's see what happens when we run our program. Oh, look at that. The different regions within the world are colored based upon the various color values that we selected. It works! Now let's see how we can use a graduated symbol renderer to display different colors based on population bands. So to do that, we're just going to comment out all of this code we wrote here and add some more code to the bottom. To use population bands, we'll have to set up a list of ranges where each range has a minimum and a maximum value and an associated color. Once again, we'll create a symbol based on each range's color. We'll then set up a QGIS renderer range object based on the minimum and maximum value and the symbol we created. Now finally, we'll use a graduated symbol renderer to choose the range to use based on that POP 2005 attribute and tell the map to redraw itself. Let's try running this and see what happens. As you can see, I've chosen different shades of red to give you an indication of each population range. In this video, we wrote a script that makes use of categorized symbol renderers and graduated symbol renderers to use different colors for different features on the map based on the value of an attribute. In the next video, we will create a map tool that lets the user click on 2 points on the map and calculates the real-world distance between those 2 points. In the previous video, we saw how to vary the colors used to draw a map's features by using a categorized symbol renderer or a graduated symbol renderer. In this video, we will learn how to create a custom map tool that lets the user click and drag to identify 2 points, and then calculates and displays the real-world distance between those 2 points. This will show us how map tools work and how to create your own custom behavior that can be installed as a map tool within QGIS. Let's start by creating a Python script to hold our code. we're going to call this maptool.py. Yeah. In QGIS, all of the user's interaction with the map takes place through map tools. We're going to create a custom map tool, which is a subclass of QGIS map tool. We'll call our custom map tool Distance Calculator. Here we go. As you can see, we have an init method here, which has to call the init method of the superclass to initialize the map tool. And it has to provide a map reference to the map canvas. We're also storing a copy of the iFace variable so we can access it ourselves. Now, even though this map tool hasn't been written yet, let's write the Python code to activate it. Pretty simple. We instantiate a copy of the distance calculator object, and then what we do is we tell the map canvas to set the current map tool to our tool. Now, because we've put the call to set map tool at the top level of our script, running this script will have the effect of activating the map tool. Let's add some methods to our map tool to respond when the user presses the mouse button and when they release it again. Now, the canvas press event method is called when the user clicks on the map canvas. The parameter here is an event object, which includes, among other things, the X and Y coordinate that the user clicked on. Unfortunately, the X and Y coordinate is measured in pixels on the screen rather than locations within the map. So the first thing we have to do is transform this coordinate from screen pixels into the map's coordinate reference system. So let's do that now. Here we are. As you can see, we're storing the transformed coordinate, which is in map coordinates, into the self.start point instance variable. That's all we need to do for the canvas press event. Because each mouse press is followed by the user releasing the mouse button, we just store the location the user clicked at and use that when the user releases the mouse button again. Now let's implement that canvas release event method. The first thing we have to do is calculate the point where the user released the mouse button, again measured in map coordinates. Yeah. Now that we've got the start and end points, both of them measured in map coordinates, we can use a QGIS distance area object to calculate the real-world distance between the 2 points. Now notice here that we're dividing the resulting calculated distance by 1,000. This is because the QGIS distance area object returns the distance in meters, but we want to display the distance in kilometers. So now that we've got the calculated distance, let's display it to the user using the QGIS message bar. Now this completes our program. Let's see what happens when we run it. It doesn't seem to do much, but let's see if I click and drag on part of the map here. And it tells us that it's 282 kilometers between those 2 points. In this video, we created a custom map tool that lets the user click and drag to identify 2 points on the map. We then calculated the distance between those 2 points and displayed the results to the user. This showed us how map tools work and how you can use a QGIS map tool subclass to respond as the user interacts with the map. This is the last video in this section. In this section, we used the PyQGIS library to solve a range of real-world geospatial programming problems. We saw how to read and analyze a raster format digital elevation model or DEM file. We learned how to read, manipulate, and write vector format data stored in shapefiles. We learned how to use different types of symbol renderers to color a map based on attribute values. And we created a map tool that responds to the user clicking and dragging on the map to calculate the distance between 2 points. This completes this section of the video course. Bye for now. In the next section, we will look in depth at the process of developing and deploying QGIS plugins. Hello, welcome to section 4, Creating QGIS Plugins. In this section, we'll learn about QGIS Python plugins in more depth. We'll see how plugins work by creating a simple Hello World style plugin, learn how to develop and distribute plugins, and then create a plugin that does something useful. We'll finish with a discussion of the types of things you can do with plugins and some of the limitations you might encounter. In this video, we will create a simple Python plugin to see what is involved in writing your own plugins for QGIS. We're going to write a plugin from scratch and then see what happens when we run it. We'll look at how you can deal with various errors that might occur while running a plugin, and finally add a toolbar icon to our plugin so you can see the various ways in which a plugin can be accessed, as well as learning about plugin resources. We'll start by creating the directory which will hold our plugin's source code. For now, we're going to store this directly inside the QGIS plugin directory. It is. Create a folder and call it test plugin. Make it a bit bigger so you can see it. Our folder is currently empty, but we're going to put some things in there now. First of all, we need to create what's called a metadata file. Now the metadata file describes the plugin. I'm going to quickly add some basic metadata to this file. Close it. Now, because plugins are Python packages, we need to have a package initialization file. Plugin standard init.py file. We're going to use this file to define our plugin. We're going to define a function called class factory. This function creates and returns an instance of our plugin class. We'll load that plugin class from a separate module, and then we're going to create and return an instance of that class. So, as you can see, we use the iFace. Yes, the iFace. As you can see, we have the iFace parameter passed to our class factory function, and we're just directly passing that into the initializer for our plugin. Let's now create the test plugin itself. The first thing we're going to need to do is import the libraries that we'll need, also define the plugin class itself. As you can see, we've set up our initializer function to take the iFace parameter, which we then store into an instance variable. We next need to create a method called init.GUI. This method defines the GUI for our plugin. We're going to create an action which we'll call run. We then connect that action to a method called onRun. When the action is performed, this action will be called. When the action is performed, this method will be called. Finally, we'll add this action as an item to the QGIS plugin menu. All this means that the user will see a menu item called test plugin, and when this menu item is selected, our onRun method will be called. The next thing we need to do is have our plugin remove itself from the user interface if the user uninstalls the plugin. This is done using the unload method. Since we added a menu item in our init.GUI method, our unload method is going to have to remove that menu item again. Okay. Now there's only one more method to define, our onRun method. For our test plugin, this is going to be very basic. All we do is display an information box saying Hello World. Now this is actually a complete plugin. Let's try it out. Save it. Start up QGIS. Manage and install plugins. If we look for our plugin, there it is here. And as you can see, it's installed. Over here, you can see that we're displaying the metadata that we created in our metadata.txt file. So we have our plugin installed. It seems to be working. Let's have a look. Plugins, here we are, test plugin, run. So let's see what happens when we run it. Oh look, hello world, just like we expected. So this is what happens when the plugin works. Let's see what happens if it doesn't work. We'll go back to our plugin source code. Quit out of QGIS to do this. We're going to make a deliberate error in our program. We're going to misspell information. Here we are. Now, what will happen when we try running our plugin now? Let's try running our plugin. What happens? Oh look, it tells us an error occurred, which is what we expect. And if you click on stack trace, it displays a standard traceback in a nicely formatted window. There is, however, another type of error you might encounter. If the plugin can't even be loaded, then an error won't appear in a window like this, but instead you'll get a message in the QGIS log messages panel. Let's have a look at how this works. edit our metadata file and deliberately misspell something. Here we go, name is spelled wrong. So now if I try to start up QGIS, let's have a look. The plugin isn't even there and no message appeared telling me that something was wrong. What I need to do is go down to View, Panels, Log Messages panel, and under the Plugins tab, there'll be an entry here. Here we go. Error when reading metadata of plugin test plugin. So it told us that the plugin couldn't be loaded because of a problem with the metadata. It's not a very precise error message. It doesn't tell us what was wrong with the metadata, but at least we know where to look. Now let's finish our plugin by adding a toolbar icon. Quit out of here. So we'll start now by first of all fixing the two mistakes we made earlier, because we do want our plugin to be able to run. We're going to need a suitable image file to use for a toolbar icon. Now I've downloaded this nice little smiley face here. You can use any image file you like as long as it's PNG format and is 24 by 24 pixels. Call this icon.png. So now let's update our plugin to use this icon. Up here, we need to load the icon in, and then we associate the icon with the action. The action now has the icon linked to it. And there's one more thing we need to do, which is we need to add a toolbar icon for this action. Because we've added a toolbar icon, we have to remove it again when we unload the plugin. This completes our actual code, but there's one more thing that we need to do. We have to tell QGIS that our plugin uses the icon file as a resource. To do this, we have to create a new file called resources.qrc. QRC files are XML format files which describe the various resources used by a plugin. Here it is. As you can see, I've just told it that we've got inside the test plugin directory is a file called icon.png that we want to use as a resource. Now, unfortunately, QGIS can't use this directly. We have to compile the resources.qrc file into a Python module. So to do that, we're going to use the terminal here. Now, in order to be able to run the command line utilities that will allow us to compile this template, we have to do a little bit of magic here on the Mac. We have to add a couple of export statements here. That will allow us to access the compile command, which is called pyrcc4. Create resources py file out of the resources QRC file. There we go. If you have a look at this file here, you'll see that it contains a compiled version of the icon file, among other few other little bits and pieces that will let it work. Now there's one more thing we need to do to use this resources file. We have to add an extra import statement here, so that we import the resources module. Now this is all done. Let's have a look at what happens. We'll run QGIS yet again. When he starts up, have a look at the toolbar. We now have our smiley face tool icon appearing as an item in the QGIS toolbar. And sure enough, when we click on it, it runs the plugin. While our plugin is very basic, we've actually covered a lot in this video. We saw how to create and install a plugin, how a plugin can add itself to the QGIS user interface, how plugins interact with the user, how errors in a plugin are handled, and how to deal with images and other plugin resources. In the next video, we'll take a closer look at the plugin development process and see how to develop and test plugins in a much more robust and efficient way. Welcome. In the previous video, we created a simple Hello World styled plugin to see how plugins work and how we can write one. In this video, we will learn more about the plugin development process. We'll learn how to separate our plugin's source code from the version deployed in QGIS so that we can develop plugins more efficiently. We'll see how to use Make to automate the process of building and deploying a plugin. We'll learn about the plugin reloader, which makes it quicker for us to develop and test our plugins, and we'll see how these various tools work together to produce a highly efficient plugin development cycle. To develop the plugin in the previous video, we stored the plugin's code directly inside the .qgis2/python/plugins directory. This works, but it's not a particularly good way of developing plugins. We had to restart QGIS every time we made a change, and our plugin's source code was stored next to all the other plugins you may have downloaded. A better approach is to store our plugin's source code in a separate place outside of QGIS, and then use a suitable build tool such as Make to automate the process of copying the relevant files into the QGIS plugin directory. We can also use Make to recompile our resources file and do anything else that needs to be done to prepare our plugin before it is run. Then, when the plugin has been built, we can use a plugin reloader to reload our plugin so that our changes take effect, instead of having to quit and restart QGIS every time. This will let us develop and test plugins much more efficiently. Let's see how we can use Make to automate the process of building and deploying the test plugin we wrote in the previous video. First of all, we'll move our test plugin into a more convenient place. In this case, I'm just going to put it on the desktop. Let's remove the temporary files that aren't part of our source code. Let's see how we can use Make to automate the process of building and deploying the test plugin we wrote in the previous video. We'll move our test plugin into a more convenient location. In this case, I'll put it on the desktop. Now let's remove the temporary files that aren't part of our plugin source code. PYC files, and also the resources.py file, which is compiled out of the template file. So we'll get rid of those files. Now we're going to create a new file, which we call makefile. Capital M. Now, this file is going to contain instructions for building and deploying our plugin. We're going to start by defining some important variables. Firstly, the name of our plugin. Then we'll add a list of the Python source files which are used by the plugin. See, there's only 2 of them. Next, we'll need a list of the extra files which the plugin requires. And finally, we need to have a list of the resources files which need to be compiled. Now that we've defined these variables, we need to set up some rules that tell Make how to build the plugin. By default, we want Make to deploy the plugin. We next have to tell Make which files need to be compiled, in this case, the resource file. Next, we have to tell Make how to compile these resources file. We set up a rule which says that the Python module is dependent on the QRC template file with the same name. And that we now want to use the pyrcc4 command line program to build the Python module from the template. To do this, we first have to set up some environment variables so that pyrcc4 can be used. Go. Now that we know what's involved in compiling the plugin, let's write the rule for deploying it. Notice how the deploy rule lists the compile rule as a dependency. This means that every time we deploy the plugin, the makefile will compile it first so that our deployed plugin will always be up to date. Once it's been compiled, we have to copy the relevant files from the source directory into the QGIS plugin directory. Before we can do that, we have to create the plugin directory if it doesn't already exist. Once it's been compiled, we have to copy the relevant files from the source directory into the QGIS plugin directory. Before we can do that, we have to create the plugin directory if it doesn't already exist. Then we copy the Python source files, the compiled resource files, and any extra files from the source directory into the plugins directory. Now there's one more thing our makefile needs to do. We want to set up a rule for cleaning up by deleting our... There's one more thing our makefile needs to do. We want to set up a rule for cleaning up by deleting our temporary files. This will remove the .py version of the QRC template files we compiled. Now, let's try this out. As you can see, we have our source code in this directory here, and this is the QGIS plugins directory here, and our plugin isn't there yet. So what we need to do now is go to the open up a terminal window, cd to the appropriate directory, which is on my desktop, and type make. As you can see, it compiled the plugin, creating the py resources.py file, and then copied it into the plugins directory. Now the beauty of make is that the process here is entirely automated. You don't have to remember to compile your template whenever you change it, and you can keep your plugin's source code separate from QGIS itself. If you use UI template files in your plugin, you also won't forget to compile them after you make changes. All you have to do is type make and everything will be rebuilt and reinstalled for you. Now that we have an automated system for building and deploying our plugin, let's see how the plugin reloader can be used to reload the plugin whenever you make a change. This will save you from having to quit and restart QGIS every time. Now ironically, the plugin reloader is itself a plugin. So let's install it. Here it is. Now, click on install and then close. Here's the plugin reloader drop-down menu. Now the first thing we have to do is tell which plugin we want to be loading. So we're going to reload our test plugin. And now from here on, we simply click on the icon and it reloads the plugin whenever we make a change. So now we've seen how to efficiently develop plugins by storing the source code elsewhere and using a make file to automate the process of compiling and deploying the plugin to QGIS. We've also seen how we can use the plugin reloader to reload the plugin so that our changes will take effect. Let's now see how all these pieces fit together to create a highly efficient plugin development cycle. We start by editing the plugin's source code in our source directory, implementing various features and making changes. Once we're happy with the changes we've made, we then run the make tool to recompile and deploy our plugin to QGIS. We then switch to QGIS and use the plugin reloader to reload our plugin so that our changes will take effect. We can then test our code to see how it works, and based on our testing, we can then make further changes to the source code, and so on. This is a highly productive cycle for developing plugins for QGIS. In this video, we learned how to effectively develop plugins for QGIS. We saw how to store our plugin's source code in a separate directory and use a make file to compile and deploy our plugin into QGIS. We also learned about the plugin reloader and saw how these various pieces form a highly productive plugin development cycle. In the next video, we will take our plugin development to the next level by learning how to prepare and distribute your plugin so that other people can use it. Hello! In the previous video, we learned how to effectively develop and test plugins. In this video, we'll see how to take a plugin that you've written and share it with other people. We'll discover the steps required before you can distribute your plugin, learn about plugin help files and how to write unit tests for your plugin, and see what's involved in uploading a plugin to the QGIS plugin repository. Now, if you write a plugin just for your own use, it doesn't matter what you do as long as the plugin does what you want it. But if you want to share your plugin with other people, there's some extra things you need to do. Firstly, you need to make sure that the name of your plugin consists only of upper and lowercase letters, digits, underscores, and hyphens. It also can't start with a digit. Also, the plugin must have a metadata.txt file. And you need to have in this file at a minimum the name of your plugin, the minimum version of QGIS that your plugin is compatible with, a description, a version number for your plugin, your name, and your email address. If you don't do these things, then your plugin will be rejected when you try to upload it. Now, while these are the minimum things you need to do, if you want your plugin to be as useful and reliable as possible, There are some extra things you might want to consider. Let's look at a couple of these, plugin help files and unit tests. We'll start by adding a help file to our test plugin. Plugin help files are HTML formatted files containing documentation for your plugin. These can get pretty sophisticated with multiple help files and multiple sections within each file, and even help files translated into different languages. But the basics are actually pretty straightforward. Let's create a simple help file for our plugin. Now we're going to create a new empty file called help.html. Edit this file, and as you can see, it's empty. Now, I'm sure that you've seen HTML formatted files before, but don't worry if you haven't. They're pretty straightforward. Here's the basic structure for an HTML file. Now we're going to add a simple heading here and some body text. Not a very useful help file, but you get the idea. Now this completes the help file for our plugin. So let's update our plugin to use it. What we need to do, tell our plugin that we want to add a help item to the plugin's menu. Then, because we've added a new item to the menu, we need to remove it if the user unloads the plugin. And finally, we're going to need to have a new method at the end called onHelp. Now, onHelp is what gets called when the user selects the help item from the menu bar. Now, to show the online help that we wrote earlier, we're going to make use of a function called qgis.utils.show plugin help. There are lots of parameters you could pass to this function, but because we're keeping things very simple, there's only one we need, and that's the name of the file. Now, we don't put the .html on the end of the file because QGIS adds that for us. Next, we need to update our make file to copy the new help file into the plugin. And it's just an extra file, so we're just going to go help.html, an extra file to be copied. Let's now try running our plugin and see how it works. So just type make, and it copies the plugin in. And we go to QGIS. We'll reload the plugin, and let's have a look at that plugin menu. Oh look, we've now got a help item here. What happens if we select help? It opens up a web browser, and there's our help file. Now, there's a lot more you can do with plugin help files. You could use this to create and display a complete online manual for your plugin. You could have different parts of your plugin access different help files when the user clicks on a little help icon. Whatever you want to do. But this is enough to get you started. Plugin help files are important because you can use them to explain how your plugin works or to add online help for specific features. If you want your plugin to be easy to use and popular with your users, then it's a really good idea to include some well-written and useful help files along with your plugin. Of course, a plugin is only useful if it works. If your plugin is buggy, or if a change in one part of your plugin causes another part to stop working, then your users will give up on it. Unit testing is a very common way of making sure that your program code works as it should. We're not going to talk too much about the theory behind unit testing here. Instead, we'll see how you can use unit testing within a QGIS plugin. Unit tests are run outside of QGIS itself using an external application which sets up the QGIS environment, runs your test code, and then cleans up again afterwards. Let's see how this can be done. Now imagine that we have a method within our test plugin that we want to test. I'm going to create a dummy method here. Simple binary search function. This is just searches through an ordered list of entries for a particular item and returns the index of the desired value within the list. Now imagine that we want to write a unit test for this binary search function that's part of our plugin. Let's create a new module to hold our unit tests. Again, we'll start with a blank file, and I'm going to call it tests.py. This is going to be a standalone Python program that uses the PyQGIS API. So let's import the various modules we're going to need. Here we are. We now need to create what's called a test case to hold our unit tests. For our test case to run as a standalone PyQGIS based application, we need to initialize QGIS when our tests are set up and clean up once our tests are being run. Here's how we can do this. To run our unit tests, we're going to add a couple of extra lines to the end of our module. Now, the next thing we need to do is import our plugin. To do this, and to allow the various parts of the plugin to work, we need to modify sys.path to include the plugin's parent directory before we import the plugin package. Here's how we do that. Now that we've imported the plugin package, we next need to call the class factory function to get an instance of the plugin. So let's see how we do that. But we immediately hit into a bit of a problem here. The class factory function requires a copy of the iFace variable that gives the plugin access to the QGIS user interface. But we're running these unit tests in an external environment where the QGIS UI isn't available. To work around this, we're going to create a fake iFace that fools the plugin into thinking that it's running within QGIS while it's actually just being used for unit testing. Let's create a very basic iFace class for our program. This fake iFace doesn't do anything at all. It's a completely empty class. But you can get example code that implements all of the standard methods of the QGIS interface class so that your plugin will work, with a few limitations, within the unit tests. But since we're not testing anything that relies on the iFace variable, we can ignore all this. Now with this fake iFace, we can now update our setup method to create an instance of the iFace of the QGIS interface. And then we can pass that class factory function and get a copy of our plugin. So now that we've got access to our plugin, the next thing we want to do is write a simple unit test something within the plugin. Add a little bit more code here. Now, the test plugin function is an actual test, and this is an actual unit test for our plugin. As you can see, we're checking that the binary search function, when passed these particular parameters, returns the value 1. This is a very simple unit test, but you get the idea. To run the unit test, all we need to do is set up our environment variables like we did in an earlier video. And then we can run, just like we can run our tests program just like we run any other PyQGIS based app. Takes a moment to come up. Now unfortunately there's a slight glitch in QGIS at the moment where it comes up with an error message here. These errors here are nothing to do with our plugins at all. It's just complaining that we haven't initialized the SQLite driver for our program, but we're not using SQLite, so we can just ignore this. What's interesting is the bits below here where it tells us that it ran one unit test and it was okay. It means the test passed. Now that you've created your application, added online documentation and tested it, let's see what's involved in distributing it so that other people can make use of it. All we need to do is remove all our temporary files, which we can do using a very simple make clean. Then we can compress the entire plugin directory. I'm just going to compress it into a zip format archive. We can now submit that zip archive to the official QGIS plugin repository. To do that, we're just going to go to plugins.qgis.org. Down here, go to the QGIS plugin repository, share a plugin, and now if you don't have an account, you're going to have to sign in. You can sign up and create an account. You have to identify yourself before you get to this page. Actually, I'm just going to edit this so I don't get that. I shouldn't have had that. We can now submit our zip archive to the official QGIS plugin repository. So we're going to go to plugins.qgis.org. Down here, go to the plugin repository, share a plugin, and the first thing it needs to do is it's asking us for your ID. You can easily create one of these. It doesn't cost anything. You just need to identify yourself. So you have an account with QGIS. and it comes up here and gives us the option to upload our plugin. Now what we do is just choose the zip archive file we created, click on upload, and it will be uploaded. Now, it doesn't just automatically get added to the plugin repository. There's a vetting process, and it can take up to 2 weeks for your plugin to be verified. There's actually a bunch of useful information on the website describing what you need to do to make sure that your plugin will be accepted. Once it has been accepted, then anyone can download and install it directly using the Manage and Install Plugins command in QGIS. In this video, we looked at what is involved in preparing and distributing your plugins. We learned about the minimum requirements for a plugin to be accepted, saw how to create online documentation and help files for your plugin, and how to write unit tests. Finally, we looked at what is involved in submitting a plugin to the official QGIS plugin repository. In the next video, we will apply what we've learned to create a geometry info plugin that provides useful information about a geometry when the user clicks on the map. Hello and welcome to the video Writing a Useful Plugin. In the previous video, we saw what's involved in preparing a QGIS plugin for distribution so you can share it with other people. In this video, we will create a more sophisticated plugin called Geometry Info. We'll create the plugin along with an associated makefile, learn how to use a map tool within a plugin, see how to identify the feature that the user clicked on, and calculate and display information about the clicked on geometry. The plugin we're going to create will let the user click on a map feature within the main QGIS window and display information about the geometry associated with that feature. We're going to call our new plugin Geometry Info. Start by creating a folder, appropriate name. Now we need to have a package initialization file for our plugin. Start with a blank file. In.py. Now, this is all very standard. Don't seen all this before. Next, we're going to need a metadata.txt file. And once again, just having standard metadata for our plugin. Next, we need an icon, and here I've got an icon I downloaded earlier. Now, any icon will do for this plugin, which is a 24 by 24 pixel PNG format image. Next, we're going to need the resources.qrc file. And once again, it's just a standard resources file telling it QGIS that we want to use the plugin. Next, we want to create a make file to automate the process of building and deploying our plugin. Let's just create that. Now, there shouldn't be any surprises here. This is all exactly as we've seen it previously. All I've done is change the name of the plugin at the top. Now finally, we're going to create the Python module which will hold our actual plugin. This plugin.py. Now we're going to start by basically duplicating the code that we used earlier. There it is. The only difference is that I've added a few extra import statements up here at the top. The onClick method, of course, is a placeholder for our actual code. Just to make sure that we've got it right, let's try running our plugin. So we'll open up a terminal window here, cd to the plugin, run make. Now that we've built our plugin, installed it into QGIS, let's start up QGIS. See what happens. Here we are. Manage and install plugins. And there is the plugin we created. And as you can see, it's already been installed. There's our icon plugin. Now, when we click on this, all that happens is it says click, which is exactly what we expected. So far, so good. Now, next thing we need to do is make it change our plugin so that it acts like a mode within QGIS. If the user clicks on our icon, the icon should be highlighted, and it should stay highlighted until the user chooses a different mode. To do this, we need to make our action checkable. This is how we do it. We now want to respond to the user checking and unchecking our toolbar icon. To do this, we'll replace information box line here with a bit of extra code. Now, if the user has unchecked the toolbar icon, then we want to deactivate our map tool. Otherwise, we want to call setChecked to activate the toolbar icon and then activate the map tool itself. This means that clicking on the toolbar icon will activate the map tool, while clicking on it again or choosing a different checkable icon will deactivate the map tool. We're now ready to implement the map tool itself. Earlier, we saw how map tools can be used to respond to various events within the map canvas. For this plugin, we're going to use a subclass of QGIS map tool called QGIS Map Tool Identify. This class makes it easy to find the feature or features at a given point. Let's create our QGIS Map Tool Identify subclass. And here it is. When the user releases the mouse button here, we want to identify the feature the user clicked on. To do this, we're going to use the identify method, searching for the first vector format feature at the point where the user clicked. If there are any, then we want to extract that feature and its associated geometry. Now, once we have the geometry, we want to analyze it and then display the information we've calculated. This process is a little involved, so we'll put the necessary code into a separate method. Because we're calculating lots of different information, we're going to use a dictionary to store the information as we calculate it, using a distinct key for each value that we want to calculate, and then display the contents of that dictionary. Here's how we're going to do it. Now, the next thing we need to do is implement that analyze geometry method. Down here. Geometries are actually rather complicated objects. There are different types of geometries, and some geometries can contain other geometries, so we're going to end up with a fairly involved recursive method to analyze a geometry. Because we want to calculate the length of a line geometry or the area of a polygon, we'll need to use a QGIS distance area object. Let's initialize this object now, using the information from the map layer to tell us which coordinate reference system the calculator should use. We're also going to create a small helper function here. This helper function adds a number to a dictionary entry and creates that entry if it doesn't exist. This will make it easier for us to update that info dictionary as we go along. Now we need to know what type of geometry we're dealing with. If we've got a multi-part geometry, for example a multi-line string geometry collection, then we need to recursively process each of the subgeometries in turn. You can see we're now calling analyze geometry again on the subgeometry so that it can be processed. Now we're left dealing with non-multi-part geometries. Next, for point geometries, we just want to count up how many points we've encountered, which is pretty simple. So we add 1, we're adding 1 to the entry called numPoints. For line geometries, we want to keep track of how many lines there are as well as their total length. As you can see, we're using the calculator to calculate the length of the line in meters, and we're storing that into the tot line length dictionary entry. And finally, for polygon geometries, we want to keep track of the number of polygons we've encountered, their area, and their perimeter. There we go. Now that we have a map tool, let's use it. Where we want to deactivate the map tool, what we're going to do is delete it. So we unset the map tool and then delete the map tool we created. Now to activate the map tool, what we're going to do is we're going to create it, associate it with our action, and then tell the map canvas to use it. Let's try out our program. Now, load a project, and I'm just going to click somewhere here. Here we are. As you can see, it's working. It's showing us the various values it calculates, but they're not very particularly pretty or helpful information. All the information is here, but it's pretty hard to read. The numbers displayed are too precise and too big. We're showing the lengths as a fractional number of meters, which is a bit ridiculous for these. Look at this, the total area here. It's just a totally ridiculous number. So what we need to do is we want to divide the length by 1,000 to get the length in kilometers rather than meters. And similarly, we want to divide the area by 1,000,000 to get square kilometers. We're also going to get rid of those annoying fractional numbers. So let's do that. To do that, what we do is down here, when we calculate the length, divide by 1,000, calculate the area, we want to divide by 1,000,000, and likewise when we calculate the perimeter, we want to divide by 1,000. Okay, now the last thing we want to do is we want to change the way we're displaying this information so it's a little bit more friendly. At the moment we just used that represent built-in function to convert a dictionary to a string, but it's kind of, the dictionary keys are a little bit ugly to read, so what we're going to do is add a little bit of code here to nicely format our output here. Now don't worry too much about this code. What we're doing here is just setting up labels to display for each of the fields and adding a suffix where appropriate, displaying the results in a message box. Now that we've done all this, let's go back, rebuild our plugin, reload our plugin, and try calling it again. There we are. Now, as you can see, the information is now being displayed in a much more friendly way that makes sense. It shows you the units, the unuseful units, and it's nicely formatted. In this video, we created a useful plugin that displays statistics about a clicked-on geometry. In creating this plugin, we saw how to use a map tool to create a mode for a plugin. We saw how to identify a clicked-on feature, how to calculate various statistics about a geometry, and how to format those statistics so they can be shown in a user-friendly way. In the next video, we will explore some of the possibilities and limitations involved in implementing your mapping application as QGIS plugins.
Hello, and welcome to this video called The Possibilities and Limitations of Plugins. In the previous video, we created a useful QGIS plugin that displays information about a geometry when you click on it. In this video, we'll summarize the types of things you can do with a QGIS plugin, how a plugin fits into the overall QGIS system and how it appears to the end user, and discuss some of the limitations and possible problems you might encounter when implementing a mapping application as a QGIS plugin. Let's take a look at some of the things you can do with QGIS plugins using Python. As you've already seen, we can create custom map tools that capture mouse events as the user interacts with the map canvas and responds accordingly. We can also write plugins that act as a geoprocessing engine, prompting the user to select spatial data and manipulate it in various ways, saving the results to an output file. We can create what are called map canvas items. These draw directly on top of the map canvas. For example, this compass rose is implemented as a map canvas item. We can create our own custom map layer by subclassing QGIS plugin layer. This lets you draw directly onto the map canvas as a separate. We can create our own custom map layer by subclassing QGIS plugin layer. This lets you draw directly onto the map canvas as a separate map layer. You can intercept standard QGIS events using signal handlers. This lets your plugin respond when various things happen, such as the map canvas being redrawn, the project being saved, the user editing a feature, and the like. Your signal handler can do whatever it likes in response to these events. Your plugin can also create map layers programmatically, setting up the data provider and creating symbols and renderers to control how the map layer is displayed. You can also create your own custom data within your program, as well as writing your own symbols and renderers to completely control the information and how it is shown. Finally, you can use the QGIS Map Composer to combine rendered map layers, labels, legends, tables, etc. to produce a complex map layout which you can then view on screen, print, or save to a file on disk. Now that you've seen some of the possibilities, let's have a look at some of the limitations of QGIS plugins. The biggest one you've probably already seen yourself. You can't create a turnkey mapping application using QGIS plugins. A plugin runs as an add-on to the QGIS application and shares the full QGIS user interface and menu structure. You can't hide away all of this complexity to create your own custom mapping system.
Because a plugin runs within QGIS itself, there are many points of contact between the plugin's code and the QGIS environment. This makes plugins more susceptible to breaking as the QGIS application changes, something that happened to a lot of plugins with the transition from QGIS 1.8 to QGIS version 2. Finally, plugins use the QGIS built-in Python interpreter. This means that you can't use any third-party libraries that aren't already built into that Python interpreter. If you need to use a library that's written purely in Python, then you can embed that library as part of your plugin. But any libraries that rely on C extension modules simply can't be used by QGIS plugins. This completes our review of the possibilities and limitations of QGIS plugins. As you can see, there are lots of exciting things you can do with plugins, but also some serious limitations, the biggest of which is the fact that you can't create turnkey mapping applications using QGIS plugins. In this section, we learned all about QGIS plugins. We created a simple Hello World styled plugin, learned how to set up an effective development cycle for writing plugins. We saw what is involved in preparing your plugin and then distributing it so other people can use it. We created a more sophisticated plugin that displays information about a clicked-on geometry. And finally, we reviewed some of the major possibilities and limitations of writing geospatial programs as QGIS plugins. In the next section, we'll look at the other main way in which you can use QGIS to write Python programs by creating external applications that use the PyQGIS library. Hello, welcome to section 6, using QGIS in an external application. In the previous section, we looked at how to write QGIS plugins. We saw how plugins can be written in Python and learned about the possibilities and limitations of writing geospatial programs as QGIS plugins. In this section, we'll see how to create a sophisticated mapping application as an external Python program built on top of the PyQGIS API. We'll work our way through the design and implementation of a turnkey mapping application called LEX. Because you need to design an application before you can build it, in this first video we'll start by designing our turnkey mapping application. This will give us the design and also give us a chance to download the data that we need to start implementing our application. We're going to start by looking at the application and what it will do. We'll then list the various requirements for this application in more detail so that we can use these requirements as we design and implement the system. We'll then lay out the details of the user interface, creating a simple mock-up so that we can imagine what the application will look like. Finally, because our application will depend on some freely available geospatial data, we'll go and download that data so that we have it ready to use. Imagine that you wanted an application that shows you where various landmarks are, and when you click on a landmark, it shows you detailed information about the clicked-on landmark. This is the basic idea behind our turnkey mapping application, which we'll call Landmark Explorer or LEX. Our application will combine two freely available sets of geospatial data, a high-resolution map that we can use to show the location of each landmark, and a database of place names that tells us where each landmark is, as well as additional details about each landmark that we want to display when the user clicks on it. Now that we have an idea of what our application will do, let's take a closer look at some of the main requirements for our mapping application. First and foremost, it needs to run as a turnkey application. Running the launcher script must start up the PyQt-based program, load all the data, and present a complete working application to the user. The user interface must look professional, with keyboard shortcuts and good-looking toolbar icons. When the user clicks on a landmark, the application needs to display useful information, including the name, the jurisdiction, that is, which part of the world the landmark is in, the time zone, and the latitude and longitude. Finally, we want our application to behave and look similar to Google Maps. This is an important point because QGIS itself is quite a complicated user interface, and we don't want to bring that complexity into the LEX application. Most users are already familiar with Google Maps, so we're going to use that as the basis for our application's behavior rather than using the default logic provided by QGIS. Let's now create a mock-up of our application's user interface. This will let us visualize how the application will appear to the end user. Our application's window is going to be named Landmark Explorer. This window will have a toolbar with various icons in it, and the main part of the window will show a map canvas. In the toolbar, we'll have standard zoom in and zoom out controls, just like in Google Maps. We'll also have icons that can be used to switch between the application's two modes. First, pan mode lets the user click and drag to show various parts of the map. And explore mode, this lets the user click on a landmark to display information about it. So much for our window. Let's now design our application's menu bar. To make our application as professional as possible, every command that can be accessed from the toolbar will also have a menu item and an associated keyboard shortcut. This will allow experienced users to quickly work with the application. We'll have a total of 3 menus: File, View, and Mode. The File menu is pretty basic, just a command to quit the application with its usual keyboard shortcut. The View menu will include keyboard shortcuts for the zoom in and zoom out commands, as well as options to show or hide the base map and the landmarks on the map canvas. Finally, the Mode menu will let the user quickly switch between our two modes using keyboard shortcuts. So this gives us the overall design for our application. We have a menu bar with 3 menus, and a window with a toolbar, various toolbar icons, and a map canvas. Now this design is enough for us to start coding. Before we do so though, we're going to need to download the data that our application will use. Let's do that now. We're going to use data from the Natural Earth website. Download the high resolution 1 to 10 million scale base map. So it's raster format data. Now there's various types of base maps we can download if we want. We're going to use the Natural Earth 1 dataset. And down the bottom here is a version of Natural Earth 1 with shaded relief, water and drainages. This looks quite good, so we're going to use it. Download the large size. This gives us the base map on which our landmarks can be displayed. For the landmarks themselves, we're going to use the Natural Earth's website's Populated Places dataset. So, downloads, again high resolution, this time the cultural link. And if we scroll down, Populated Places, there it is there, download Populated Places. Now once we finish downloading, we'll end up with these 2 zip archives. Let's move these somewhere convenient and decompress them. There we go, these 2 folders. Now to make them more convenient to use, we're going to put these inside a new directory called data. There we are. In this video, we came up with the idea for a Landmark Explorer program, which we're going to call LEX. We listed the various requirements for this program and then designed the program's user interface. Finally, we downloaded the geospatial data that our program will make use of. In the next video, we will start writing the framework for the LEX application and then implement the overall user interface for our program. In the previous video, we designed our Landmark Explorer application called LEX. In this video, we're going to start implementing the LEX application by writing the main program along with a platform-specific startup script. We'll then define the application's main window and the various menus for the application, add the resources we'll need, and finish by connecting the various toolbar and menu actions to placeholder methods within the main window class. Let's start by creating a folder to hold our application's source code. Now we're going to move the data that we downloaded earlier into this folder. We next want to create our application's main program, which we'll call lex.py. We're going to use the same basic structure that we used earlier for a standalone program using QGIS. We'll start by importing the various libraries we'll need. We then create our application object and initialize the QGIS environment running the application until the user quits. We then clean up and exit. Now that we've got our application set up, we next want to create our application's window. Let's create this as a QMainWindow subclass. As you can see, we've called our subclass LexWindow, given it the title Landmark Explorer, and set the initial size for our window. Let's now change our program so that it creates and shows a Lex window when the application starts. We start by creating the window itself. Then we want to show the window. And finally, we want to bring the window to the front. Now, this is all we need to do with this file right now. Because this needs to be a turnkey mapping application, we will need to create a startup script that sets the appropriate environment variables and then runs our lex.py program using the Python interpreter. How we do this depends on which operating system you are running. For MS Windows, you'll create a run.bat file containing these instructions here. For Mac OS, you'll create a run.sh file containing these instructions. And for Linux, you'll create a run.sh file containing instructions that look a bit like this. Because I'm running on a Mac, I'll need to create a run.sh file. And these are the instructions I'm going to need to put in them here. Now to use this startup script, I'm going to need to make it executable. And once I've done that, I can simply run the program like this. As you can see, our startup script ran the lex.py program, and it's now displaying a blank window. This is a great start, as it gives us something to add our user interface to. Now unfortunately, we're going to have to ignore these errors that come up in the terminal window. This is an annoying quirk of the current version of QGIS, and there's nothing that we can really do about it. Now let's start working on that user interface. We're going to create a new module which we're going to call UI-LexWindow.py. Now we're basically mimicking the structure of the templates created by Qt Designer without having to use the point-and-click designer, which gets messy and harder to follow. We'll start our module by importing the libraries we need and defining the UI-LexWindow class. Now this setup UI method is where we'll create our application's user interface. We'll start by giving the window a title. And we'll then create the main part of our window called the central widget. This is just a placeholder at the moment, but this is where our map canvas will go. We next want to set up our menu bar. As you can see, we have three menus: File, View, and Mode. We now want to create the toolbar at the top of our window. Now that we have a menu bar and a toolbar, let's create the various actions for our system. We'll start with an easy one: quit. We next want actions to show or hide the base map and landmark map layers. As you can see, we're using this method setCheckable here. This makes the actions so that they can be checked and unchecked by the user. Next, we want the zoom in and zoom out commands. As you can see here, we've set an icon for these commands, and we're going to create these icons shortly. We next need the pan action. This action lets the user switch into panning mode. Once again, this is checkable because we want this action to be persistent. That is, it stays checked until the user switches to a different mode. Our final action is the explore action. This lets the user switch to explore mode. Once again, this is a checkable action. Now that we have all our actions, let's add these actions to the menus that we defined earlier. We'll start by placing the quit action into the file menu. We then add the various actions to our view menu. And lastly, we'll add the actions to our mode menu. Now that we've set up our menus, let's also add our actions to the toolbar. We're going to have 4 actions in our toolbar. There's only one more thing we need to do to this file which is to tell the window to resize itself to fit around its contents. Now this completes our uilxwindow.py module. In our user interface template, we referred to 4 different icon files. We're going to need to get these icons somehow. I actually downloaded these icons from the QGIS source code repository on GitHub, but they needed to be converted from SVG format into PNG, which was a bit messy. You can either use your own icons, or else grab a copy of these icons, which are available as part of the source code that you can download for this video course. Here are the icons that we need. Now I'm going to put these into the icons directory inside our main program directory. We now have to tell PyQt that these icon files are resources used by our application. To do this, we'll create a resources.qrc file. Now here's the necessary resource description. To use this file, we'll have to compile it into a resources.py module. Do that using the terminal. We saw how to do this earlier, and now we have here this Python module that can be imported. Now that we've created our UI template, let's change our main program so that it uses it. First, we're going to have to import our UI template. We next want to change our Lex window to use the template class. Now, we're using multiple inheritance here, so that the Lex window class inherits from both the Q main window and our UI Lex window template class. Now we can tell our window to initialize itself. Now we can tell our window to initialize itself by loading its contents from the template. Now let's try running our program. As you can see, we now have a complete user interface for our application. All the toolbar icons are there, and we have our menu set up as well. Of course, nothing actually does anything yet. Our next task is to connect our various actions to methods that will perform these actions. So let's do this now. We're going to put this behavior into our main program. We'll start by adding some placeholder methods to our Lex window class. We can now connect the various actions to these placeholder methods. As you can see, the quit action is calling qapp.quit, which is a standard way of quitting a PyQt-based application. The other actions call our various placeholder methods. We'll be implementing these placeholder methods in later videos in this section. In this video, we created the main program for our Lex application. We then created a startup script so that it can act as a turnkey mapping system, and then began to define our user interface. We created the UI template module and its associated resources, giving us a complete, though non-functioning interface for our system. In the next video, we'll add a map canvas to our program, using that canvas to display the base map and landmark map layers. In the previous video, we began to implement the Lex application, setting up the overall structure for our program and defining the application's user interface. In this video, we'll start to draw the map that makes up the main part of our application's window. We will add a map canvas to our window, load the underlying map data to be displayed, learn how to show and hide map layers in response to the user's actions, and see how to draw a label beside each landmark. Let's start by adding the map canvas to our window. If you look at our UI template, you'll see that we defined an instance variable called central widget. This represents the central part of our window, where our map canvas will go. Now let's add a map canvas to our central widget. This extra code is going to go to at the end of our init method. Our next task is to load the data into our map canvas. We're going to have two separate map layers, a raster base map layer and a vector landmark layer. To implement this, we're going to create a new method called loadMap. This method will create the two map layers and add them to the map layer registry. Once the two map layers have been created, we'll then show the currently visible map layers by calling another method called showVisibleMapLayers. Finally, we'll set the visible extent of our map canvas so that the app initially shows just the continental USA. Let's now write that showVisibleMapLayers method. We've already got two actions set up, Action Show Base Map Layer and Action Show Landmark Layer. These let the user toggle the two map layers. Since these actions are checkable, all we need to do is see if the action is currently checked by the user, and if so, add that layer to the list of visible layers. Notice that we're adding the landmark map layer first, and then the base map. This ensures that the landmarks appear in front of the base map. Now we need to tell our program to load the map when the application starts up. Next, we want to check our two actions so that the map shows both layers when the program first starts up. And finally, we want to tell our program to recalculate the list of visible map layers whenever the user checks or unchecks our map layer actions. So, show base map layer. So, let's try running the program and see if it works. As you can see, the map canvas is now showing both the base map and all our landmarks. If we go here and uncheck one of these, it will be turned on or off. So far so good. For each landmark, as you can see, we're just displaying a simple coloured dot. This isn't very useful as the user has no idea what each landmark is. So let's add a label to each of these landmarks. Now we're going to use something called the PAL labeling engine, PAL. We can use this to draw labels. Using PAL labeling is a bit involved. We have to access the PAL layer settings from our landmark layer, modify these settings to tell the labeling engine how to label our various features, and then save those settings back into the landmark layer again. Now that we've configured the settings for the PAL labeling engine, we need to tell our map canvas to use it. In theory, this should label every point on the map. Let's try it out. As you can see, it works. But there's a problem. There are just too many landmarks, and the labels are all unreadable. Now don't worry, we'll fix this, but doing so is a little bit involved and it requires us to be able to zoom in and out. So we're going to have to leave this until the next video. In this video, we added a map canvas to our program. We loaded the base map and landmark map layers from our data files on disk and saw how to show or hide these map layers based on the user's selection. We then began the process of adding labels to the various landmarks. In the next video, we'll continue to add functionality to our program by implementing the pan and zoom functions. Once we have zooming in place, we'll be able to fix that problem of having too many labels to display by adding a zoom-specific filter to our landmark layer. In the previous video, we added a map canvas to our application, adding functionality to display a base map and the landmark map layer. We implemented the ability to toggle these on and off, and also added a label for each landmark. In this video, we will continue to add functionality to our application by implementing the ability to zoom in and out and to pan the map. Once we have zooming implemented, we'll then be able to add a zoom level specific filter to our landmark layer to avoid the problem we saw earlier where there are too many labels displayed at once, making the map unreadable. Let's now implement the zoom in and zoom out actions. In QGIS itself, these are implemented as custom map tools so that you switch to the zoom in mode and then click on the map to zoom in. But if you remember, one of our requirements for the Lex application was that it should work in the same way as Google Maps, and Google Maps doesn't zoom like this. Instead, simply clicking on the zoom in tool zooms you in, and clicking on zoom out zooms you out. There isn't a zoom in mode or a zoom out mode at all. We're going to emulate that behavior in our Lex application, and fortunately doing this is really easy. All we need to do is when we have the zoom in action, we just tell our map canvas to zoom in. And likewise here, the zoom out action tells the map canvas to zoom out. Right, let's now implement the ability to pan the map. Panning, that is, clicking and dragging on the map to move around, is another area where QGIS is more complicated than we would like. In QGIS, you have a pan tool that has lots of features. For example, clicking anywhere on the map will recenter the map around the clicked on point. This can be quite confusing for new users, so we're going to implement our own custom panning tool that is much simpler. As you can see, we're creating a QGIS map tool subclass named Pan Tool. This tool will implement our panning mode. In our init method, we're simply telling the map tool to use an open hand cursor when this tool is active. We next want to respond when the user clicks and drags on the map. This is pretty straightforward as the map canvas already supports the notion of panning, so we just tell the canvas to pan the map when the user presses the left or main mouse button. When the user releases the mouse button, we also have to tell the map canvas to finish panning. Here's how we do this. Now that we have our map panning class, we have to create an instance of our pan tool and associate it with our pan action. With that done, we can implement our set pan mode. As you can see, selecting the pan action activates the pan map tool. The last thing we want to do is select the panning mode when the application first starts up. Now let's try out a program to see how it works. As you can see, the pan mode is now selected by default. And if we click and drag, pans just like we expect it to. Also, the zoom in and zoom out buttons work. Well, our application is starting to take shape. So let's now deal with this pesky labeling problem. As you can see, there are just too many labels shown at once and the map's looking really ugly. To solve this, we're going to filter the landmarks based on the current zoom level. Our landmark data set includes an attribute called scale rank. It is a simple number in the range 0 to 10, where the largest landmarks have a scale rank value of 0 and the smallest landmarks have a scale rank value of 10. QGIS has a thing called a scale denominator, which indicates the scale of the map that is being shown. For example, at 1 to 100 million scale, you can see the entire world at once, while at 1 to 2 million scale, you can only see the island of Sicily. The second part of this number, the 100 million, the 10 million, and so on, this is called the denominator, and is used by QGIS to identify a zoom level. We're going to use this to filter the landmarks based on their scale rank and the current zoom level's scale denominator. We will set up a rule so that each landmark is shown only over a certain range of scale denominator values. For example, a landmark with scale rank 2 will be shown whenever the scale denominator is between 0 and 10 million. Notice that the minimum is always set to 0. This ensures that the larger landmarks are still visible as the user zooms in. Now, to make this work, we're going to use what's called a rule-based renderer that controls which features are going to be visible. To use this renderer, we're going to need to extract what's called the root rule from the renderer and then duplicate it, modifying the rule to suit our needs. The code's a little ugly, but it's not too hard to understand. We have a default rule that we clone. We then modify the cloned rule and then add it back into the root rule again. At the end, we're going to remove the default rule from the root, leaving only the rules that we've modified. So now let's set up our first rule. In this rule, we say that for landmarks with scale rank 0 to 1, we only want to display these features when the scale denominator is between 0 and 100 million. This means that these landmarks will be visible when the map is zoomed right in and also when it's zoomed out to show the entire world. If you remember, these features are the largest ones. Now for the second rule, we're going to show landmarks with a scale rank of 2 to 4 when the scale denominator is no more than 10 million. For the third rule, we'll show landmarks with scale ranks 5 to 7 if the scale denominator is no more than 5 million. And finally, we'll show landmarks with a scale rank of between 8 and 10 if the scale denominator is no more than 2 million. There's only one more thing that we need to do, which is to tell the landmark layer to use our new renderer. Now let's try this out. As you can see, now only some of the landmarks are being displayed, according to the rules that we set up. And as we zoom in, wow, more landmarks become visible. It's working. Now there's one more nice feature we'd like to add to our program. Since we have a scale rank for each landmark, it'd be nice to use a larger font size for the larger landmarks. To do this, we can use a case expression to calculate the font size based on the scale rank. So all we do is set up the expression. Instead of hardwiring the font size, we use our expression. Now let's see what happens when we run the program again. As you can see, it worked. The larger landmarks have a larger font size. The result looks quite nice. In this video, we implemented panning and zooming for our Lex application. We then solved the problem of having too many labels to display by adding a rule-based renderer to our landmark layer, and finished by adjusting the font size to use for the labels based on the size of the landmark. In the next video, we'll implement the final feature in our application, which is Explore mode. In the previous video, we added panning and zooming to our application, as well as filtering landmarks based on the current zoom level. In this video, we will implement the final feature of our system, an Explore mode where the user can click to display information about a landmark. To do this, we'll need to implement a new Explore map tool, add support for the Explore mode within our application, and then link all the various parts together. Finally, we'll test our application to make sure that it works. Let's start by creating our Explore map tool. This tool will be a subclass of QGIS map tool identify. As we saw in an earlier video, we can use this class to respond when the user clicks on a feature within a vector map layer. That's exactly what we're going to do here. As you can see, our initializer function takes a reference to our Lex window as a parameter. We're going to need this later when we display information to the user about the clicked on landmark. Just as we did before, we're going to use a canvas release event to respond when the user releases the mouse button, and use a QGIS Map Tool Identify method to identify the clicked on feature. Now that we've got the feature and its associated geometry, we can extract the information we want to display. Because we're displaying a variety of information, we'll use a list to hold the information as we calculate it. The first thing we want to do is display the name of the landmark. Because not every landmark has a name, we need to check the attribute before we add it. We next want to display the jurisdiction for the landmark. This is the name of the country and the state or region it is in. We can get this information from the landmark's attributes. Finally, we want to display the latitude and longitude for this landmark. To do this, we'll query the landmark's geometry, which is a point feature, and extract the x and y values from that point, where x corresponds to the longitude and y is the latitude. We've now collected all of the information we need in the info list. Let's display that list using a message box. This completes our Explore Map tool. To use it, we'll have to instantiate our new class. Now that we have our Explore tool, we can implement the Explore mode within our application using this tool. Now notice that we uncheck the Pan tool when the user clicks on the Explore icon. This makes the Pan and Explore modes mutually exclusive. We're going to have to do the same thing for the Pan mode. When the user clicks on the Pan icon, we have to uncheck the Explore action. This ensures that only one mode is active at a time, and the appropriate map tool is selected based on the current mode. Our program's now complete. Let's try it out. So we can click on Explore, click on a feature, and as you can see, we're now showing information about that feature. It works! In this video, we finished implementing the LEX application by adding an Explore Map tool that displays information when the user clicks on a landmark. We then used this map tool to implement the Explore mode within our application, and finished by testing the program. We now have a complete and useful mapping application, one which meets all of the requirements we listed at the start of the section. In the next video, we will summarize what we have learned about creating standalone applications using QGIS and look at some of the possibilities and limitations involved in implementing mapping applications in this way. Hello and welcome to video titled Possibilities and Limitations of External Applications. In the previous video, we finished implementing a standalone mapping application called LEX. In this video, we will review the possibilities and limitations of developing standalone mapping applications using QGIS. We'll look at the types of things you can achieve using QGIS within an external Python program. We'll look at the advantages of developing mapping applications in this way, and we'll finish by examining the main limitations and challenges you might encounter when you use QGIS in a standalone Python program. Let's start by looking at some of the things you can do with QGIS in a standalone Python program. As we saw with the LEX application, it's possible to use a map canvas to display an interactive map on the screen. As we saw with the LEX application, it's possible to use a map canvas to display an interactive map on the screen. We can use QGIS to load geospatial data from a data source, to create new geospatial data, to manipulate geospatial data, and to save it. You can also create custom map tools that let the user edit or interact with spatial features on the map. You can use tools such as QGIS Distance Area and the QGIS Network Analysis Library to perform complex analysis on geospatial data. And, as we saw earlier, It's quite possible to create your own turnkey mapping applications with complete control over the user interface. Let's now take a look at some of the advantages of using PyQGIS in this way. External applications give you complete control over the look and feel of your application. You can control everything, from the menus and toolbar icons to the colors and symbols used to draw information onto the map. In terms of look and feel, there's no limit on what you can do. This lets you create a truly customized mapping application. Your application will only include the features that you want, and you don't have to shoehorn your application into an existing user interface like you do with QGIS plugins. Finally, you can access almost the entire PyQGIS library. There are some limitations due to the fact that the QGIS interface class and its cohorts can only be used within the QGIS application itself, but you can use any other part of the comprehensive PyQGIS library within your standalone program. Let's now look at some of the limitations and challenges you might encounter when developing standalone mapping applications using PyQGIS. As we've already mentioned, you can't access QGIS interface or the iFace variable or any other class such as QGIS message bar that depends on the QGIS user interface. You also can't access QGIS plugins from within an external application, as these depend on the iFace variable being present. As they say, with great power comes great responsibility. Because you can build the entire UI yourself, you have to build it completely from scratch. This can take a while, as the UI for a sophisticated mapping application can be quite complicated. Finally, the fact that your Python program depends on the PyQGIS library that is built into the QGIS application makes it tricky to create a double-clickable installer for your program. There is one PyQGIS application for Windows that has successfully extracted the required PyQGIS libraries and installs them separately, but this is a very involved process and there's currently no solution for doing this on Mac OS or Linux. The PyQGIS developers suggest either asking your users to install QGIS before running your program, or else bundling the entire QGIS application into your program so that both get installed at the same time. Getting all these various parts installed and running on a user's computer is quite a challenging task, especially if you're trying to support multiple platforms. In this video, we looked at some of the possibilities, advantages and limitations of using the PyQGIS library within a standalone Python program. This completes this current section. In this section, we designed and implemented a standalone mapping application named Lex that lets you view and explore various landmarks around the world. We designed the application in detail, downloaded suitable data for our application to use, and then began coding. We saw how to use a map canvas within a standalone mapping application and created our own panning and zooming modes so that they worked the way we wanted them to. We then implemented Explore mode, where the user can click on a feature to display information about it. Finally, we summarized what we have learned and how this applies to developing PyQGIS-based applications in general. This is the final section of this course. I hope you've enjoyed it.